Okay. Hi, everyone. My name is Leland Richardson. I'm a software engineer working on the Android UI toolkit at Google. More specifically, I work on Jetpack Compose. And today I'm going to talk to you about the Compose compiler and the Compose runtime. So I'm kind of curious, brief show of hands. How many of you before this conference had heard of Compose? All right. How many of you had used Compose? OK, cool. All right, well, it's not everybody. So let's first start by going over what Compose is kind of at a high level. So first and foremost, Compose is a declarative runtime geared towards UI development. And it's 100% written in Kotlin. And interestingly, Compose requires a Kotlin compiler plugin. And this is a lot about what we're going to talk about today. So there'll be more on that later. It's built by the Android UI toolkit team. So this is the same team that currently maintains the existing UI toolkit. And it's a complete ground-up rewrite, a reimagining of what a UI framework on Android would look like, and especially in a declarative way. And critically, it's unbundled from the Android operating system. So it's a user space library, and that allows us to ship out-of-band updates. And it means that if you want to use Compose, you don't have to wait for OEMs to adopt new features from OS releases. And also, it's open source. So this is kind of a cool thing. So we're developing all of Compose completely out in the open. And these are live commits. And so you can go and check out, look at the source, contribute, understand how things work, things like that. And importantly, it's really, really early. So Compose right now is what we call a developer preview. And what that means is that there's still big chunks missing. There's still things that we have yet to do. And there's still a lot of fundamental changes that we're likely to make before it becomes production ready. So OK, as I mentioned, Compose is a declarative UI runtime. And it's also a Kotlin compiler plugin. And so you might see this and think, well, why do we need a Kotlin compiler plugin to just build a UI library? That seems like a pretty big leap there. There should be a pretty high bar to actually go in and touch the compiler to build something like this. And so this is going to be a lot of what I talk about. And hopefully by the end of this talk, you'll understand a little bit more about what we're doing with this compiler plugin and why. And so this is maybe a good time for me to just give a few caveats about this talk. So I'm going to go over some pretty advanced topics today. And really, the goal is to go over these with the goal to have it be fairly approachable to people who don't understand or work in this type of environment every day. At least that's the hope. And additionally, I'm going to talk about a lot of implementation details. So these are things that you don't necessarily need to understand in order to use Compose. And more importantly, a lot of these things are liable to change. And some of the things that I'm talking about aren't actually done yet. And so these are sort of planned things. And so just keep that in mind. OK, so first, let's go over what we mean when we say declarative. Compose is a declarative UI runtime, but what does that actually mean? And usually when we talk about declarative, we're talking about it in the context or in contrast to something being imperative. And so let's go over what that is by means of an example. So let's consider we have an application. It has some sort of a unread messages icon. And so in this application, what we want to do is we want to say, OK, if there are no unread messages, just an envelope. And if there are some unread messages, we show a paper and a badge. And then we're going to do something a little bit cute. If you've got over 100 unread messages, we're going to render some fire on it. So how would we implement this in an imperative UI framework? It might look something like this. So this is completely platform agnostic. This is just pseudocode. But what you would do in an imperative system is you might write a function that takes in the new count. And then what it does is it looks at the current state of the UI. And it checks to see what that is, and then what it should be. And then it makes some changes as a result of those things. And so you actually have to go through all these different cases and make sure that you're adding and removing and updating all the right things. And so this fairly simple example actually ends up with kind of error-prone code. It's very complicated. And in reality, it might actually even be more complicated than that. Sometimes what we need to do is we need to separate the initialization code or sort of the first rendering from the updating code. So doing the same thing in a declarative system might look something a little more like this. And so the idea here is that just like before, we have a function that's receiving a new count. But in this case, the key difference is that we aren't actually looking at what the current state of the UI is. All we're saying is, given this count, here's what I want. So okay, here I want an envelope, and if count's greater than 99, show fire. If count's greater than 0, show paper. And then inside of it, we're going to render a badge if it's greater than 0, and it's going to have a count. So the kind of name of the game with a declarative UI system is that you want to describe what your UI should look like right now, but for any value of now. It needs to work for all of those things. And so what that means is that you write code that's independent of the previous state, even though it handles all of the states for all time. So going back to this example, let's sort of look at the anatomy of this function. It receives count as data coming in. And we want to treat this data as immutable data. This is just a transform function of data coming in. Here's the UI that we produce out. And so here we're calling other composable functions, in this case, envelope and badge. And this represents our description of what the UI should look like as a result. And it's important to note that we're able to use any sort of language features that we normally would in any old function. And so here we're using an if statement, for example. But you're able to use other things like for loops or any sort of utility functions or libraries that you're used to using inside of Kotlin. And then it's also important to note that we're leveraging Kotlin's trailing lambda syntax here. So envelope has a composable lambda parameter that we're passing in at the end. And what we're doing is we're using that to create some sort of an implicit structure in the UI. And so envelope here is semantically wrapping the badge that is being rendered inside of it. And then finally, we're annotating this function with @composable. And so from this example, it's not quite clear yet why this is necessary. But this annotation is what we use to indicate that it's one of these declarative functions. And so I want to go in and talk about what this is actually doing. What does @composable actually mean? And what does it actually do? Why do we need it? And so to do that, I want to talk about @composable in contrast or as an analogy to something else, which is the suspend language keyword. So the suspend keyword alters function types. And so you're able to use suspend in front of a function declaration, you're able to use it in front of a lambda declaration, or you're able to use it on a function type. And @composable is able to be used in all of the same places in exactly the same way. And the important thing to understand here is that just like suspend, @composable is actually changing the type of that function. And so what that means, practically speaking, is that if you had a composable unit lambda and you tried to pass it into a function that was expecting a unit lambda, it would not compile. The type system would complain because they're different types. The other thing to think about is the suspend has this thing where you can't call a suspend function unless you're inside of a suspend function. And this is because suspend functions require a calling context. There's an object that's passed around through all of the suspend function calls. And it turns out that composable has the same exact constraint for a very similar reason. We also pass around a context object. That means that you need to be inside of a composable function in order to call one. So now let's go and look at the motivation for suspend. Here we have an example of sequential asynchronous operations that we're trying to do without suspend. And what happens when we do something like this is that we have a bunch of nested lambdas that create an environment where it's difficult for us to utilize language features like for and if, and it's difficult for us to follow the logic of what's happening. And it turns out that if you turn it into something like this, it's a little bit easier to follow and maps closer to our mental model of what's actually going on when we have sequential asynchronous operations. And so with composable, there's a similar motivation, which is where we want to take these types of functions that are mapping sort of new data and updating UIs. What we want to do is we want to take this and essentially turn it into this. And so the way to think, or the way I like to think of suspend functions is that they're just like normal functions, except they have a few extra capabilities and semantics. So it's a normal function, except execution can pause and resume at any time. And while it's paused, the thread is unblocked. And so that creates a semantic difference from other functions that you might use, but you're still able to use them and think about them in a similar fashion. So composable functions, in the same sort of framing, are normal functions, except they have this extra capability, which is that there's a sort of memory of the last call at that position in the call graph. And additionally, a composable function can be re-invoked at any time. And so this first capability, this memory, it's closely related to a concept that we call positional memoization. And I'm going to go in and talk about exactly what that is. And then this ability to be re-invoked at any time is something that we call recomposition. I'm going to talk about that as well. So looking at positional memoization, it's important to understand some of the data structures that we use for compose. And in particular, that object that I was talking about, that calling context object that we pass around, there's a data structure inside of that object that we use that's very similar to a data structure known as a gap buffer. And most of you probably aren't familiar with gap buffers. They're not very commonly used, but sometimes they're used in text editors. And so the data structure works something like this. Oh, and we call this data structure a slot table. So here we have our slot table. And a slot table is basically a representation of a list. And this list is a list that has a current index. And in this case, we're representing this list as a flat array in memory. And so necessarily that array is larger than the data that the list represents. And so the space in that array that is empty, we refer to as the gap. And so if we're passing this object around all of our composable functions, as we're executing composable functions, we might be able to appeal to this data structure. And we're able to store data into it. We can insert data as we go along and execute. And then when we're done, at some later time, we may recompose that function like I mentioned. And when we do that, what we want to do is we want to reset the current index to the same index that it was previously. And so now, as we execute the function again, we can choose to skip over data if we want, make no change, or we're able to update a piece of data if we'd like to. And then if the structure of execution is changed, what we can do is we can insert new data into that data structure. And when we do that, we move the gap to the current index, and then we're able to insert data in constant time. And so the key thing to kind of understand here is that all of the array operations that we've been talking about, so like get, insert, and remove, those are all constant time operations. The only thing that's not constant time is moving the gap. And that happens whenever there's a structural change. So the core bet that we're making here as framework developers is that the actual structure of UIs don't change very often. What UIs tend to be very dynamic in that there are lots of values changing all the time, but the actual structure doesn't change all that often. And when it does, it's usually a big change, so it comes in big chunks, and then paying the cost of moving the gap at that time is worth it. And so that's sort of the key trade-off here that we're making. So let's go ahead and look at what this works out to be in practice. So here we have this composable function, which is just a counter. And let's see what the compiler does when it encounters this function. So if we desugar this a little bit, what the addComposable annotation means is that we're going to add this synthetic parameter here, which I've named as composer. And we're also going to insert composer start and end calls in the function. And you can see here that there are these key integers that get passed in. And we're also passing in these seemingly magic integers to the other composable function calls, which in this case are state and button. And the way to think about these integers, they're generated by the compiler, but basically you want to think of it as a unique identifier for that call site. And so one possible implementation would be to just take a hash of the source position that call site is at. Additionally, what we're doing is we're passing in the composer object that was passed to us. We're passing that in to all of the other composable functions that are in our body. So let's go over and look and see how this function with this new compiled code interacts with the slot table. So the first thing that we do is we hit this composer.start. And with that, what we do is we insert a group into the slot table. And that group has the key that was passed into that function. And then we move on and we go to the call to state. And state is also a composable function, and it's also going to insert its own group. And then the implementation of state is going to store a state instance into the slot table as well, and then return it. And then we run into button, and button is going to insert its own group. And each of the parameters that we pass to button are going to be stored in the slot table as well. And then button itself might have its own implementation that itself utilizes the slot table in some way. So I'm representing that here. And then now we're done executing this function, and our slot table is filled. So let's look at this. We basically see that there's some section of the slot table that is allocated towards the call to state. And there's another section that's allocated towards the call to button. And we can see that overall, this section here is allocated towards the call to counter. So this linear representation in the slot table is sort of like a depth-first traversal of the composable call graph. And we might look at this and we say, okay, we're inserting an awful lot of these groups here, and what are they actually used for? And so the groups are needed to do structural modifications, like we talked about. But structural modifications only happen if you have essentially conditional logic or some sort of control flow that could cause changes as executions go on. But it turns out that we're a compiler, so we can actually know statically when a certain composable call might happen conditionally. And that's most of the time not going to be the case. So actually, we can elide these groups most of the time. And that really limits the amount of space that we take up in the slot table, and so that's a good thing. But let's look at an example where we do need the groups. In this case, we have this app composable that goes and fetches some data somewhere, and the result of that is either null or not. If it's null, we're going to show some sort of a loading screen, and if it's not null, then we'll render this header and body as a result. So when we desugar this code, it might look something like this. And we see here that instead of passing the key through the composable calls, what we're able to do is we're just able to insert groups around control flow, in this case, the if statement. And so we have a different group for each branch. So now let's imagine that we're executing this function, and the first time we execute it, getData returns null. And so that means that we're going to go down the first branch of this function, and so we'll insert a group with key 1, 2, 3, and then we'll call loading, and then we're done. So the next time that app gets called, let's imagine that result now returns something non-null. So we're going to go down a different path. We're going to go down the ladder branch. And this is where the interesting thing happens. So here we're calling composer.start with key 4, 5, 6. And what the runtime is going to do is it's going to look at that, and it's going to compare it with the current group, which is 1, 2, 3. And it's going to see that it's changed. And so that lets the runtime know that a structural change is happening. And so what it needs to do is it needs to first move the gap to the current position, and then wipe away all of the data that was in the current group, and then essentially continue execution as normal. And so what we see here is that one of the ways to interpret this is that the overhead of the if statement in compose is a single entry in the slot table. And what this allows us to do is have a backend cache, which is the slot table, that has its current index guaranteed to be at the same point of execution every time it is there. And that actually ends up being a really powerful tool. And so we utilize this to create what we called positional memoization. And memoization is sort of like a fancy word for essentially caching the result of a function based on the inputs of that function. And so to give an example of something more closely related to that, let's consider this example, where here we have this composable function, and inside of it, we're doing a calculation. We're taking in the items and the query string that was passed to us, and then we're filtering it based on that query string somehow. So this is a CPU-intensive operation. And one of the things that we could do is we could wrap it with this call to remember. And remember here is a composable function that essentially memoizes something. So if we go through and look at how this would work, we make this call to remember, and the first argument is items. And the first time we're executing this code, we're going to store the parameters that were passed to us. So we're going to store items in the slot table, and we're going to store the query in the slot table. And since this is the first time we're executing, we don't know what the result of the calculation is. So we go ahead and run the calculation. And then we're going to store the result of that calculation as well, and then return it. So at this point, nothing really that special happened. But the next time we execute this function, something interesting takes place. So here we have a call to remember again, and we have a populated slot table. And let's assume that items and query haven't changed. So what remember is going to do is it's going to look at items, it's going to compare it with the previous version. And then it's going to move forward and it's going to compare query with the previous version of query. If both of those parameters compared equal to the previous version, then the entire calculation gets skipped. And we just return the result that was stored in the slot table. And this is essentially what memoization is, except memoization usually happens in a global scope, whereas this is more of a local scope, where we have a single shallow cache that is local to its position in the call graph. So the signature to remember might look something like this. And if you look at it, there's a pretty interesting degenerate case, which is where there are no inputs. So in this case, we can imagine kind of this weird example where we take remember, and the calculation that we're remembering here is a call to math.random. And math.random is an inherently impure function. And so with a global memoization strategy, this would kind of be nonsensical. There'd be no reason to do it. But here it actually takes on a new meaning. In this case, x is going to have a unique value for every execution of example that happens at that position. But if we use example multiple times in our hierarchy, each version of example that we use is going to have its own answer for what x is. And so you can think of this as basically a type of persistence that we've created. And the really interesting thing is that this persistence gives rise to what we would think of as state. And so the state function that we were using earlier, it's actually a utility method around remember, where we're just remembering the allocation of a state instance. So that brings us to recomposition. And I mentioned earlier that composable functions have this ability to re-invoke themselves at any time. And so I want to go over exactly how that works and why we would do that. So here we have our same counter example. And in this case, what happens is we first call state, and state returns us this new instance of a state object. And the state class is annotated with @model. And what @model essentially means in this context is it's a special class where compose can observe reads and writes to the properties of that class. So what's going to happen is as we execute counter, if we see that anyone makes a read to a model instance during the execution of the function, what we can do is we can automatically subscribe counter to writes to that object. And so when someone writes to that object, we can schedule a recomposition which will cause counter to get composed again. And so you can see here in the onPress of button, we write to the state variable. And so that sounds all well and good, but how do we actually do this? And so if we look at what the compiler is doing, when we desugar this function again, we're going to call start and end, just like we did before. But this time, we're going to add this code to our end call. And what we're doing here is composer.end is optionally returning some value. And it would return null in the case where no model object was read during the execution of it. Because if we know for sure that there's no way that this composable would ever get recomposed, then there's no reason for us to spend time teaching the runtime how to recompose it. So if composer.end is non-null, we end up calling this update scope function. And we pass it a lambda, and that lambda is basically just calling counter again. And this time it's calling it with a new composer, and that composer is understood to have the right current index so that when it recomposes, it does so properly. And so whenever we talk about a composable recomposing, what's really happening is this lambda is getting called. And so we can leverage this capability to do some pretty interesting things. Here's an example bind method that we might write today in the current UI toolkit for Android. In this case, what we're doing is we have a function that receives a live data instance of messages. And what we want to do is we want to make our UI reactive to changes to that messages. So what we do is we observe that live data instance, and we pass it a lifecycle owner, and then a lambda. And that lambda is going to get invoked every time messages changes. And so to write this in the lambda, we have to then, inside that lambda, go and update our UI. With compose, we can do something a little bit different. We can kind of invert this relationship a little bit. So we can have a similar function where we have a composable and it accepts this live data. And in this case, what we're going to do is we're going to call a different observe method. This one is a composable observe method. And this is going to do two things. So one, it's going to return the current value of live messages. And then the other thing it's going to do is it's going to subscribe that composable to updates to that live data instance. And so instead of passing a lifecycle owner and a lambda that updates or that runs every time the live data changes, what we're doing is we're leveraging the fact that composables are restartable and just saying we'll restart this composable every time it changes. And so if we wanted to implement that observe function, it might look something like this. So just like before, we're creating this state variable, and we're calling it result. And then we're returning from that function the value of that state variable. And then what we're doing is we're calling this onCommit composable. And what this is a way to run work whenever compose has made a change, if something else has changed. And so in this case, we're passing in the live data instance. So we're saying, run this work for every live data instance that this function gets called with. And so the work that we're doing is we're building an observer, and that observer is going to mutate the state variable that we had created whenever it gets called. And then we're observing the live data instance that we're operating on. And then the final thing we do is we call this onDispose method, and that essentially does a teardown of everything that we set up in the onCommit. And so this will get called whenever compose knows that it no longer needs to use this function. So in this case, we're removing our observer and cleaning up after ourselves. And so this type of pattern you could use to have compose interop with any sort of state management or reactive library that you're using. This is kind of how you could achieve that interop. Okay, so let's talk a little bit about some performance optimizations that we can do. Here's an example of some simple composables. In this case, we have this Google composable, which renders an address form, and we render some text nodes with that address. It's a simple example, but let's look at what happens to the slot table when we do this. So in this case, we're storing all of the parameters to these composable calls in the slot table. And we can see that there's actually a little bit of redundancy. Here we have Mountain View and CA that is stored up top from the call to address, and then stored again later down the call graph to call text. And so we want to try and get rid of some of this redundancy. And it turns out that since we have a lot of static understanding, we can get rid of a lot of this. So let's imagine that we have this Google composable, and in addition to the composer parameter that we're inserting, we also add this static parameter. And what it is an integer bit field. And what the bit field represents is for each bit, it's essentially a flag indicating whether or not the parameter at that index the runtime has deemed will never be different. It will be static for as long as this function executes. And so we can do some interesting things here. We see that the last 4 arguments to address are static. We're rendering string literals here. So those are always going to be static. And then the first parameter, number, it's going to be static if my parent told me that it was static. So if we go down into address and we do the same thing, we can see that we can add some somewhat non-trivial Boolean logic to each of these text calls. And understanding this logic is not important, it's not the point. This is the type of thing that compilers are really, really good at. It's this tedious, deterministic logic that humans don't need to read. So we're doing it at compile time, and you don't need to worry about it. So if we go back to our original example, we can see that we had this redundant Mountain View and CA stored, and so we can get rid of that. And then we see that all of the remaining strings that were stored, those are actually static. They're string literals, so we can get rid of those as well. So that means that this entire hierarchy, the only thing that we need to store is the number parameter. And so then if we go into the Google composable, what we see is that since number is the only thing that we need to check, we could actually generate code that checks it ahead of time. And if it hasn't changed, it can kind of know that, well, I don't need to call address at all. And we can just skip the execution of address altogether. So this is a pretty significant thing. What this means is that I could write a composable call, and the compiler is going to generate code that may not call it every time that code is executed. And so that's a pretty big semantic leap. And so I want to talk about a computer science concept that this is related to, and it's called referential transparency. And this is sort of a big sounding word, but most of you actually have probably already taken advantage of this fact if you've ever taken a basic algebra course. And so if we want to understand this better, what referential transparency means is that when I look at this mathematical expression here, what I see is, okay, I'm calculating 3 squared and 4 squared, and I know that that is equal to 9 and 16 respectively. So I can, in my head, replace that expression with just those constants. And then I know that 9 plus 16 is equal to 25. So in my head, I'm going to replace that with 25. And then I know that the square root of 25 is 5, so I'm going to replace that with 5. And so what we've done is we've, in our heads, simplified something more complex by essentially leveraging the fact that mathematical functions are referentially transparent. So it means I can replace the result with the expression itself without changing the behavior of the program. And so the ingredients for something to be referentially transparent is that the function is pure and it has no side effects. And so what I mean by pure is that given the same inputs, it has the same output. And by no side effects, I essentially mean that there are no shared mutations, no observable mutations outside of the scope of the function. And so then we can ask the question, are composable functions pure and side effect free? No, not at all. But actually, if you squint just right, there's some interesting facts that we can take advantage of here. And so I was not completely upfront with you with how compose worked in some of the previous slides. And that was just to simplify things. But the truth is that when we pass in the composer to a composable function, it's actually read-only. And so all of the things I was talking about, where we're updating the value of the slot table, those side effects actually are stored in the composer as a change set to be applied later. And so what this means is that in some ways, composable functions share a lot of the same advantages that referentially transparent functions have. And this allows us to do some interesting things. But basically what it means is that we can have a loose guarantee that the call to header up here is not going to affect the call to item or to footer. And so these operate independently. And what this allows us to do is that in some cases, the compose compiler may deem a function skippable. And it may generate code that will skip that function during the execution of your call graph when it deems it to be safe. And in addition to that, what it means is that we can actually run the execution of some of these functions on different threads and run them in parallel and concurrent with one another. Because the composer that we're passing in is read-only. We're not making any changes to it. And so it's thread safe to do so. Now, this isn't how compose works today. This is a capability that compose has, but this is something that we're working on very hard to make this a reality. And a lot of the design decisions that we've made with the compose runtime have been directly to achieve this goal. And so a lot of the decisions we've made have been in that vein. Okay, so I wanted to just end with a couple of closing thoughts here. So it's an interesting question to ask. Is compose a UI library, or is it something a little bit more? And one of the ways I like to think about compose is a UI library that's built on top of a draft language feature proposal that is the compose compiler and the @composable annotation. And I think that the way we're doing things here, it's completely agnostic to UI. And there's some interesting, basically, implementations that might be related to incremental computation and some other things that you might be able to do. And so I guess I'd like to just sort of leave this talk today with kind of a challenge for you all, is to kind of think about what else we could apply such a system like this to, and have a compiler that sort of that really aggressively optimizes these very large declarative call graphs. Additionally, I just wanted to emphasize again how early this is and how there are a lot of things that are still in progress that we're still working on. And so compose while it's interesting to talk about and to play with, we really do not want you to be shipping production apps right now. There's a lot of changes that we're making. And then finally, if this is something that interests you, please come join the conversation. We actually are pretty active in the Compose channel on the Slack, on the Kotlin Lang Slack, and so I would encourage any of you to come and talk with us about certain things. I'm personally pretty active there, and a lot of the rest of the team is as well. Anyway, that's all I have. Thank you.
Should we start? Woo, it's live.
We're on. Who's going to shut the door?
Shut the doors. Hello. Hello.
Hey.
So, hello. This is Nat Pryce.
Hello. This is Duncan McGregor.
Hello. We are server-side Kotlin developers from London. We have as many years' experience as our failing eyesight and grey hairs would lead you to believe. And one thing over the years we've discovered, in many languages, in many systems, they're all subject to failure. Different languages have different ways of dealing with those failures, but Kotlin is, shall we say, conflicted. So we thought we'd give a talk about the error handling strategies we've used and how to choose between them.
Oh, great. Error 1, can't change slides.
Over there. Yes. Click. Click. Whee. So, if failure is not an option, what is it? My dictionary says lack of success, which just begs another question. But it also helpfully says the neglect or omission of expected or required action, which is more helpful. So let's just say failure is the inability of the system to do the job that we want it to do. It went wrong.
Yeah. So what that means is, for example, helpfully handling invalid user input, we're not counting as a failure. That's something our system should just do as part of its normal operation.
So how do programs go wrong? And when we say program, we mean functions, methods, procedures, any code that we're invoking. Well, often we don't give them the correct input they need to do their job. Sometimes they need to talk to other systems, and those other systems fail in some way, or communications with those systems fail. I have heard of programmers making errors. Apparently, they read past the end of arrays, try to get the first item of empty lists. And sometimes the environment that our systems are running in fail. We might run out of memory, not be able to load a class, those sort of things. And there are other ways of failing, but these cover most eventualities in the way we will look at things for this talk.
So it turns out that handling errors is difficult to do, and itself is very error-prone. Right? Software engineering researchers, as in people who research and study software engineers, have found that it's very common for error codes or error report signals to be lost as they travel through layers of our software stacks, and that when systems go wrong in catastrophic ways, a large majority of the time, they went wrong trying to handle recoverable errors, and the logic that was triggered to try and handle those errors contains bugs that could quite easily be caught by unit tests. Error handling is difficult to get right in the architectural level, and even difficult to get right in the small, in the logic.
Why is it hard? Well, we often don't know how and if an operation could fail, so we don't take into account the fact that it could fail. Knowledge of how to handle an error can be a long way away from where the error is detected. Errors can leave our systems in states from which we can't recover. And error handling tends to be hard to isolate from the code, from the surrounding code, and therefore it's hard to test, and therefore we don't test it.
Yeah. So if something's hard work, if it's error-prone, that's the kind of thing that I think computers were invented for. I want the computer to do the drudge work so that I can focus on the bits of the job that I enjoy more. So Kotlin inherited a lot of concepts from the JVM, from Java, and Java introduced checked exceptions when it was first defined as a method of helping programmers deal with the drudge work of handling errors and knowing that their error handling is covering all the cases. So earlier languages had introduced exceptions before then, but Java introduced them at the type level. A signature of a method would include the checked exceptions that it could possibly throw, and code that would call that function, method, would have to either propagate those exceptions or handle them in some way to pass a type checker. So that was great. Well, I think we both are among the rare breed of Java programmers that like checked exceptions.
5 or 6 of us in the world.
And you know, when I first learned Java, I remember reading a document that explained the exception system that sort of I've summarized on this slide here, where it said, okay, checked exceptions are for things that happen that can go wrong in the environment of the program. Right? Your program has to handle these kind of errors, therefore they'll be checked by the type checker. And there are other categories of errors that can happen at any time that it's not worth type checking. There are errors that a programmer makes that can be detected by the runtime. Those are reported as a runtime exception. You know, there's no point in type checking those because, well, if you knew that you would make them, you wouldn't actually make that error in the first place. And then there are errors which are reported as an error, which is where the actual runtime itself can no longer support the semantics of the language. It's failed to load a class that your programmer has to execute. Maybe it's run out of memory. And again, there's really nothing your program can do about that. The entire runtime is now untrustworthy. And thanks to mutable state, even a programming error in many cases, certainly in early Java programs, in the style that they adopted, would leave your program where the state of your program was in an unknown state, and really at that point, all bets are off. Does anyone actually recognize this categorization of Java exceptions? Has anyone ever read that document? A few people, yeah. I've never found that document again. I don't know where it went. That's how old I am.
So that was a good idea, and we loved it, but the exception class hierarchy was awkward, and after Java was released, they couldn't change it. Runtime exception became a subclass of exception, which nobody really ever understood. And from the start, Java exceptions weren't used consistently in the standard library. So URL constructors threw checked exceptions, but parsing integers from strings didn't. Assertions became an error, not a runtime exception. And it got worse over time, especially with lots and lots of open source libraries, all of which had different conventions. And in the end, popular frameworks took APIs that threw checked exceptions, wrapped them into unchecked runtimes exceptions, making absolutely everything worse. And in the end, Java just gave up, I think.
Yeah, it's pretty common now, just to throw everything as a runtime exception. And of course, higher order functions also made that more complicated.
Yes, so at the point of Java lambdas, the idea that if I'm calling a function that could throw an exception, I can also throw that type of exception. I think the language designers at that point just threw their hands up and said, it's all too messy. Nobody actually really cares about checked exceptions anymore, and they gave up.
Yeah. And now Kotlin. So Kotlin, I think, as a perfectly understandable and reasonable pragmatic design decision, doesn't have checked exceptions. Turns out that checked exceptions are a Java feature. They're not a JVM feature. And so Kotlin can throw unchecked exceptions even when Java would consider them to be a checked exception. However, at this point, we've now lost our ability to type check our exception handling code. And certainly, when I went from Java to Kotlin, that was one of the things that sort of surprised and shocked me. And we had to come up with other techniques for representing, propagating, and handling errors. And that's really what the rest of this talk is about.
So, what is the best way to handle errors in Kotlin? It's important. And how do we as Kotlin programmers get back to the consistent characterization and reporting of errors supported by the type checker that we liked so much in Java? Well, some of us liked so much in Java.
It depends. Okay? Not an ideal answer, but I'm a consultant, so that's one I give quite often. But what we're going to talk about is, what does it depend on? We all write different programs. Some of us write back-end web services. Some of us write browser-side code that compiles to JavaScript. Some of us write Android. Some of us write embedded systems. Some of us move between all these things. So, I've worked in lots of different systems of different sizes, different resource constraints. And the best way of handling errors will depend on the performance constraints of your system, your team's preferences, and many other, the wider architecture that it has to fit into. And what that depends on will change as your system evolves. So what might be a perfectly reasonable decision at the start of a project when the code is small will have to be reevaluated as your system evolves, grows, and changes and is used in wider and different contexts. And so we'll also talk a bit about that. So we want our tooling, and the type checker in particular, to help us, with our system right now, and also to help us manage the evolution as it grows and evolves, and we have to change our error handling strategies. So, what can we do? We could just throw exceptions, right? They're in the language already. We don't need to get another library. We don't have another dependency that we have to manage. So there's a lot of benefit of just using exceptions because they're built in. They're very easy to throw, and in fact, possibly too easy to throw. What happens is that many different exception types can propagate up to code that has to handle errors and perform logic on error handling logic. And then we end up with code like this, where we do have to catch certain errors. This is an HTTP post handler. It's getting a form. It's reading a form, which might fail. It's expecting there to be an ID field in the form. It expects to be able to parse that into an integer, a big integer in this case. And it can throw either no such element if there is no form field of that value, of that name, or a number format if it's exception, if it's not a valid integer. And both of those should be reported back to the client as a 400 so that it doesn't retry an invalid request. Any other kind of exception should be reported as a 500 so that in the future it could retry the request. So that makes the error handling logic, overly verbose. We have to handle each of those cases, have some duplicated logic. So in practice, what we do is we translate errors as they cross from one bounded context, one domain in our application, maybe the domain of parsing forms, into another domain, maybe the domain of handling web requests, in a way that simplifies the exception handling logic. So we abstract the many different ways that a lower level code can fail into sort of an abstraction of that failure to simplify logic at the higher level. So here we will catch a number format exception and throw bad request. We will handle the case that a form field is not there, throw bad request, and now our HTTP layer only has to worry about bad request exceptions and doesn't really care about the exact reason that they were caused in the lower level code. And that's really one of the things we want to get across in the talk is, how do we hide and abstract different kinds of errors away and translate them for the convenience of error handling logic. However, without support of the type checker, how do we know whether we've handled and translated all of those exceptions? This is a slide I snuck in at the last minute. Duncan, there is a bug in this code, and can you spot it? Yeah, it's a trick question. It's a trick question because, of course, exceptions aren't type-checked. They're not in the signature. There's nothing in there that tells you that I've changed my code here to use JSON, not a form, and now that JSON library is throwing different exceptions. And there's nothing in my parse request that has to handle those exceptions from the JSON library, and so they bubble up to the HTTP layer, where eventually they propagate all the way up to my server implementation, and they get returned to the client as a 500, and it will then retry an invalid request. So by not type checking the propagation of errors, we have now created an architectural problem which might end up causing request storms in failure scenarios and things like that. So the logic in the small can have wider effects on the wider system across our system. That's why checked exceptions were so cool.
They were cool, but they did now. Grieve, move on.
What we do is we fuzz test our code to make sure that they only throw the exceptions that we expect them to throw. So we can't type check it, but we can test it, and fuzz testing is one of these techniques that is unreasonably effective at uncovering these kind of errors. We just take some of the good data, the good inputs that we already have in our positive test cases. We mutate it. I'm using a library here called Snodge that I wrote. It's available on GitHub, but there are other libraries that do the same thing. We mutate that input. We throw thousands of mutated copies of that input into our parser, in this case, and it might or might not fail. But we want to make sure that if it does fail, it only fails by throwing an exception that we want it to throw, and it never throws an exception that we don't want it to throw. So exceptions are fine. There's nothing wrong with exceptions within a context in which their disadvantages are not going to cause you problems. So if it's a small program, if there's a single point in your code where all exceptions are handled and have exactly the same behavior, where you don't really care about the type of the error, you don't have different logic depending on the type of the error, then exceptions are a perfectly good choice. If I'm writing a command line application, it just has to fail and return an invalid status code. If I'm writing a web handler, it can just return a 500. Maybe I can write a dialog box in a desktop application and so on. Okay? But we do have to be aware that when this context changes, we have to maybe choose a different error handling strategy. So, for example, we have some client APIs that call sort of services that are provided by other organizations and other parts of our organization. We have our local abstractions of those. If we can't communicate with one of these services, it'll throw an exception, and our code returns a 500. Great, that's fine. But then we started using this client in a batch job, and what we didn't want was an exception to propagate out of the batch job, which was handling thousands of entities rather than individual entities, and roll back the entire transaction. We wanted to be able to have logic that said, right, we will fail individual entities, but not the entire transaction, the entire batch. And we wanted that type checked, so at that point we chose no longer to use exceptions, but to expose the errors in the ways that we will look at for the rest of this talk that could be type checked. Context changed, and so we changed our design to help us use a type checker to make sure that the rest of our code was then behaving the way we wanted, and we were aware of the error cases, and the compiler was helping us stay aware of it.
Even with other techniques, though, you should probably be using exception for the JVM errors, out of memory, can't find a class, and probably program errors as well. So invalid argument, illegal state, where we haven't checked things properly. They are pretty much unrecoverable because we weren't expecting them. And we need to know as much as possible about where they happened because we weren't expecting them. And so the stack traces there in particular are really useful.
Yeah, and try and avoid swallowing exceptions or throwables, let's say, that are reporting these unrecoverable system or programmer errors. So don't catch throwable in your code because you will now be losing this information and maybe continuing with the entire system in a very broken state. It's just catch exception or the exceptions that you know that you have to catch because you've fuzz tested.
Hi. So before we go on and look at some of the what we can use in place of exceptions, let's stand back and think. Why are we doing this at all? The problem with errors is that they contaminate. If my request processing needs to parse data, and that can fail with an error, then the request either has to be able to cope without the data or fail itself. And that happens all up and down our systems, in and out of our systems. And if enough code of the leaves of the tree can fail, then every path through our code is subject to failure, and we have to choose between strategies, and we have to decide how to represent those failures and how to handle them. And in practice, this happens pretty quickly in most systems. So practically every function invocation is subject to failure, which is why Java programmers pretty soon punted and just made everything throw unchecked exception. So how about we write functions that can't fail?
How do we do that, Duncan?
Well, so our first category of errors was invalid inputs. Click. So here, fetch. Fetch will have to fail if that string can't be parsed as a URI. And so every function that called it with a string will have to deal with a failure. And if a function can't cope with all the possible values of its arguments, then it has to fail. That's often with an illegal argument exception. And we call those partial functions. They are only valid over a particular range of inputs. And the opposite is a total function. Total functions can return a result for all combinations of arguments supplied. And when we call them, we don't have to consider exceptions. Well, with the exception of
Other
I/O in this case. Yeah. So in here, we've just changed to pass a URI rather than a string. Now, we're really quite used to doing that. And if the source of the URI is a string from outside or somewhere else, and it almost always is, then it might not seem like we bought much. It's going to fail somewhere. But if we make it fail at the point where we read the string rather than the point where we need the URI, then all the intervening code doesn't have to consider the consequences of the failure. So these partial functions pollute our code, and they hide everywhere. So the fetcher here is doing two things. It's reading from config, and it's reading from config in the effectively in request processing at some point. And because the base URI config parameter may or may not exist, and it may or may not actually be a valid URI, that can fail at runtime and in the middle of normal code. We go on. And so the solution here is, once again, to pull the error-prone code to the outer layers of your system, in this case, at the point where we construct the fetcher. And in that case, fetch now becomes a total function again, and all the code that calls it doesn't have to worry about errors.
So what?
Back to other ways of errors.
Yes. So yes, we still have errors. How do we represent errors in a way that can work with a type system and allow us to type check them? That's our challenge. Now, one option is we just use nulls to represent errors. Right? The advantage of null is it's in the language. We don't need another library. The type checker will tell us when we're not handling the null case, and there is nice language support for working with nulls. Right? The disadvantage is you've only got a valid value or not a valid value, and there's no way of including any contextual information, any explanatory information to allow the system to either automatically recover from the error or to report something useful to a human operator. So it's useful for handling error cases in the very small scale pieces of our code. Parsing a string to an int or to a URI makes perfect sense to return a null because the context of that error is very small, and it's very easy just to look at the string that we parsed and to see what's wrong with it. Right? Maybe if we're parsing a large JSON document or something, that wouldn't be enough. We wouldn't be able to find the error inside that JSON document, but for small strings, that's perfectly okay.
One of the reasons this is so much nicer as a technique in Kotlin than Java is because Java, there was no way of expressing, at least in the early days, that this function could return null, and so and callers weren't forced to handle it. But of course, in Kotlin, we have nullable types.
Yes. So the fact that you can pass null into something has to express in the type system, and is therefore that function is a total function. While in Java, the fact that any type could also be null, apart from primitives, of course, means that every function in your Java program is a partial function. And this is a common convention in the standard library, so we can follow that convention. The naming convention is to say, or null at the end of a function that could fail and will report failure by returning null. It's a little bit clumsy, but it is very explicit, and so that's nice. And so we often follow this. Maybe if it's parsing a string, I might call the function parse, but that's a convention within our team's code base and something that we all agree on. And the sort of wider convention is to say to something or null. And thanks to the sort of null coalescing operator and the Elvis operator, handling these error cases is quite straightforward. Here we are looking for something that's missing, and then we're trying to parse it. And in any case, the null is an error, and so we can easily handle the error just by using the Elvis operator to say, if there's any error when I'm parsing this thing, return bad request. If there's anything, a kind of error when I'm parsing the other thing, just return bad request. So that's quite straightforward to do. And it's type checked. And it plays nicely with writing your own extension methods, because then the null coalescing operator plays nicely. It has a disadvantage that we're using the same concept, the same construct, to represent both the error case and what could be a perfectly valid absence of a value. And as soon as you have to distinguish between something that's like logic that you do when something is missing and logic that you do when there's an error, then the language support is no longer as convenient as possible. So in this case, let's look at just the first example. Here, we want to be able to provide a default value for the count parameter. And it has to be an int. If we parse the int, and that can't be parsed, that null case is an error. But if the count field is not in the form at all, that's perfectly valid, and we want to default it to 100. And you can see the logic now is looking quite a bit more complicated. And we still have library functions that are going to throw exceptions to report errors and not return null to us. And so we're going to have to convert those exceptions to null in order to follow this convention. And so we try and do that sort of as close as possible to the function that we'll throw. And also, fuzz test it to make sure that we are handling all the exceptions we expect and returning them into null and not allowing anything to propagate through that we don't expect. So using nulls is fine when the cause of an error is obvious from its context, and we don't have to represent optionality and errors in the same code and in the same bit of logic. So for example, parsing simple values as we've seen, looking up data that may not be present. Okay? And again, we have to be aware when that context is changing and then maybe use a different technique as that context changes. And we use fuzz testing to ensure that we are doing the conversion from exceptions into nulls and that we're using library functions that we're not entirely sure of their behavior in a way that is appropriate.
It's worth saying that, if you go back one, thank you, that the advantages of null also mainly extend to using an option type, but that does lose all the nice language support that Kotlin gives us, and hence the title of this talk, Failure is Not an Option. So we saw before how narrowing the types of function parameters we could make partial functions total so that we don't have to worry about errors for more of our code base. We still need to convert raw output to acceptable input at some stage, but the further to the outer edges of our system we can do that, the less code has to cope with failure. Now we can extend that to other types of errors, not just invalid data. In particular, I/O is very susceptible to errors, but we often read to and write from and write to external systems in the bowels of our code. In Java, we checked exceptions. That meant that either most of our code could throw I/O exception, or we would just lie and pretend that database calls couldn't fail and smuggle the errors in unchecked exceptions when they did. So pull the I/O up to the outer layers, read values into memory early, validate them early, transform them with total functions that return values to be written back at the outer layer. In this case, we have a function that is taking some data from a URI and writing it into a file. It's reading nicely at the top level, pulling all the data out, and then it's processing it. But you can see that process is taking file as a destination. We know that it's got to open the file. It's got to write to it. So that means that process is a function that's really should declare it's throwing I/O exception. We have to guess that it's throwing I/O exception. Another way of looking at this is that functions returning unit are suspect. We know that they must be doing something. They must have side effects, and that's often I/O, or other side effects are often subject to failure. So we can transform this code into the code on the bottom code, which basically says let's pass values down our system and pass results back as values. And if we do that, then the I/O and the things that are subject to failure can move to the outside of our system. More of our system becomes total. More of our system becomes not subject to failure. And we don't, in all those cases, we don't have to choose between exceptions or nulls or other techniques that we might find out about.
Okay. So another option that we could choose is to use what functional programmers would call an algebraic data type. In Kotlin, we call a sealed class hierarchy to represent the case that you might have a successfully computed value, or you might have a failure that was caused by some reason. Right? Here's an example. This is from some example code I wrote called result for k that turned out to be useful enough for people to start using in their production code. But it is only 3 lines of code, so fair enough. Here's an example where a result can either be a successfully computed value of type t, or an error that happened for some reason of type e, and those two cases are handled as subclasses of result, which are just simple data classes of success and failure. And of course, this is just one example of this. There are other examples in other libraries that you can obtain.
And there is a result type in the standard library, but it isn't an algebraic data type, and when you try and use it, IntelliJ complains, so probably best to ignore it.
Yeah.
It's really just seems to be used for coroutines at the moment.
Yes. Now, the advantage of using a sealed class hierarchy like this is that you're forced to handle the fact that something might fail in order to get hold of the successfully computed value. The exhaustiveness checking in the compiler will not allow you to consider the success case without also considering the failure case and doing something about it. So, which is great, that's what we want, but now just pushes the problem a little bit further and creates a new one, because what we don't want is to have that ugly code around every single function call that we call in our system, or at least any fallible function call that we call in our system. And how do we represent the failure reasons themselves to make sure that we can type check that as well?
I think we have just moved the ugly code, mind you.
Well, yeah, all code is ugly in some way. So we add or define useful functions, extension functions on that sealed class hierarchy that allow us to focus on the happy path, and let the functions collect and report and shortcut error handling when an error happens. So flatmap will take a success value and call a function that returns a result, so it might fail, resulting in the final result of that function. But if the original value being that it was called on was a failure case already, it will just result in the failure case. So we can focus on straight line processing of our logic and let the convenience operations handle the sort of propagation of errors for us until the point that we want to do something explicitly about those errors, in which case we have some convenience operators that will allow us to get hold of the error reason and do something about it. So in this case, we read some JSON, we perform a command that has some kind of outcome, and at the point we're at the map, we have either a failure or a successfully computed outcome. We want to send the outcome back to the client so we can map it into an HTTP response, which is just another data structure. It's not actually written yet. And if there's a failure, we also want to report that to the client. So we have another convenience operator, map failure, which does the equivalent for the failure branch of that sealed class hierarchy. And that will map the error reason to an HTTP response, giving us a result of either an HTTP response for the success case or an HTTP response for the failure case, which means that both branches are holding the same value, and there's another convenience operator that then just returns us back the HTTP response from either of those things. So they're both the same type, and we've now got back into a total function, and we don't have to worry about results anymore. And therefore, we can return a response back from this function.
If you're used to handling errors with exceptions, a team may balk at this for a while. You have to back into code like this gradually. So I think it's quite a sophisticated technique, but one that's worth.
Yeah. And if you've got Scala programmers, they would like, hold on, that last map and map failure and get, that's just a fold in Scala. Let's collapse it into a fold. So, I'm not as sophisticated as they are, so I'm like, I can't read that. Let's break out those different cases so I can see what my logic is. So, Now, the reason that this is so easy to read and it looks so linear is because that each pipeline step is just passing along a value to the next pipeline step, and they don't need to use steps from values from earlier in the pipeline. Here, to generate an HTTP response, we actually want to use the request and some other information from earlier on in the pipeline, and now we've got this. In order to do that, we need to nest the blocks and the flat maps, and then suddenly our code is not looking so pretty, right? That nice linear pipeline of computation is represented as deeply nested function calls, and Kotlin doesn't have language support for monadic comprehension, as functional programmers would call this stuff, and so we're just resorting to do it with functions, and it can get quite hard to read. Yeah, I tried to not mention the monad word, but I failed. Arrow has a very clever technique using coroutines for flattening out these nested flat maps into syntax that is inspired by Scala and Haskell. Very nice. We don't actually use this in production because it's still they still haven't released a 1.0 version, and the APIs are changing between releases, and so and the performance isn't optimized yet. So we're not using this at the moment. Instead, we use the fact that Kotlin's inline functions allow you to return from a lambda out from the enclosing function, named function. So we define an operator on failure that is given the failure, and we run an inline block. That means that inside that block, we can return the failure straight from the function and flatten the pipeline, right, returning back the successfully computed value, right, to just unadorned by the result wrapper. So this flattens out our logic into something that looks much more familiar to procedural programmers, but it does come at it comes with a drawback of there's quite a bit of boilerplate code to handle these particular failures. On the other hand, the control flow is now very explicit, and that makes me happy when I'm coming to code that I don't know, which is often code that I wrote a few weeks ago. So it's a trade-off, right? If you can handle the sort of API churn of Arrow as it's stabilizing, maybe that's a good choice for you. This is the choice that we've gone down.
I think this is the sweet spot for me, certainly. This plays to the strengths of Kotlin as a style and allows you to know when things are going to fail in a reasonable way.
Now, that still means that we still have to do something with those error reasons. How do we represent them? You could just represent them as an exception. I think the result type that's actually in the Coroutines library does that. Right? And then you've got a big hierarchy of exceptions, and some of those exceptions are being returned in the error branch of your seal class hierarchy. And that's still quite fast. Exceptions are slow when you throw them because the JVM builds up a representation of the stack and in the stack trace of the exception, and that can be quite slow, which is why people say don't use exceptions for flow control. But if you just create an exception, it's just an object on the heap, and so you can use them. The risk that we found there is that eventually almost everything returns a result of T or exception because there's a single unified base class for all exceptions, and it's easier just to return exception, and now you've lost the ability to check the exhaustiveness of handling all the error cases because you have to consider all the possible exceptions, and then you're back where you were when you were throwing exceptions. Right? So we prefer to create a hierarchy of sealed hierarchy of data classes to represent error cases, and then we made the mistake of having a single root type of all our error reasons, and ended up back in a situation where we could no longer type check all the possible cases because we had like a massive hierarchy of these things. So we ended up back in the same problem. Don't do that if there's anything you can learn from that. What I would do now is define small hierarchies of error cases for different bounded contexts in my application, and then explicitly translate those error cases from one type to another type as I crossed the boundary between one context and another context, so that I knew that in each place in the code, I was exhaustively handling every single possible cause of error.
Often it's enough just to have an enumeration.
Yeah, in many cases an enum is fine. Sometimes you want to associate more data with it. Do we care about the stack traces? You can have stack traces on an exception. You can't on a data class unless you jump through some hoops. It turned out, what we found is no, actually, for anything where we're explicitly reporting errors, we actually don't care where they happened. The data model has enough context about the application's processing and context for us to understand why that error happened. Exactly where it happened in the code, not really important. Right? If it's an unexpected exception, if it's a programming error, then we really do care, because we want to dig down and find out why that happened, in which case an exception thrown by the runtime is fine, and we just let that bubble up to our top-level exception handler, which will report it into our infrastructure.
6 minutes to lunch. These people are thinking they're not going to eat.
Right, so results. A result type is fine when your team are used to functional programming style, you don't need stack traces, you do want to type check your errors, and you do want to represent a little bit more context about what happened when an error happened. So propagating exceptional cases up to web pages, when you actually want to do different logic based on exactly what happened. So maybe some things are going to return in a 400 to clients versus a 500. Looking up data that may not be present, we can actually distinguish now between an error or a successfully computed but absent value, which is a valid state. And again, beware of that context changing. And just like we do with nulls, and just like we do with exceptions, we convert exceptions to failures as close as possible to the methods that throw them, and we fuzz test our code that can fail to make sure that we're not getting any unexpected exceptions thrown out of that code.
Even if you are heading down the route of an result type, it's important to remember that errors are a fact of programming life. Error can be thrown, certainly on the JVM, from any operation at any time, and so we better plan for that. So we need to design our systems to be robust to errors, and we're looking at techniques like preventing inconsistent persistent state through transactions or units of work, so that if something goes wrong, either all of our required changes are persisted or none are. We want to avoid, therefore, mutating shared state, and strive, at least, to make request processing abort leaving everything in a consistent state. And actually, the call stack is a very good way of doing that. If all your mutations are scoped to your call stack, if an exception is thrown, then they can't leak, and they'll just be discarded. Whole processes, we may kill whole processes when they detect an inconsistent state and restart them from outside. And queues and retries, patterns for making systems resilient to the failure of subsystems. But it's important to differentiate between environmental failures, where a retry is a sensible thing, and logic failures, where if you retry it, the code is going to go through the same path, and we are going to fail in the same way. So fuzz testing, chaos monkeys, plain old putting it into production, and logging exceptions will all show us where robustness is lacking in our code, and are places to introduce, probably in that case, a result monad to let us know these are possible.
So we've talked through some techniques. We've talked about the trade-offs that we found between them, and this is the sweet spot that we found for our system, being developers of server-side web applications that run in the cloud. Okay, I think. But your system is going to be different than our system, especially if you're an Android developer or writing embedded code. And so, hopefully, those options are available to you, and the trade-offs will help you find the sweet spot for your system and be aware of the context in which that sweet spot is staying sweet, and then when you might have to consider the fact that maybe a new technique is required because your context is changing, because your system is growing and being used in different contexts. Thank you very much. Some links there for you.
Good afternoon. So today I'm going to be talking about testing coroutines. But before we jump into the talk, I wanted to thank JetBrains for hosting this amazing conference in this really, really awesome venue. And thank you all for coming as well. And hello to the people on the live stream and that are going to watch the videos later. So I'm Sean McQuillan. I'm a developer advocate at Google, and I work with the Android team. Today we're going to talk about KotlinX Coroutines test, which is a library that helps you test coroutines in some simple cases as well as some advanced cases. And we'll kind of walk through a bit of both of those. Before we talk about this, I do want to really put a large disclaimer and say this library is currently an experimental coroutines API, and it may change before stable. There's many parts of the API that are being discussed being changed right now. And I just synced with some people at JetBrains, and there's some likely changes that we'll talk about as we go through this talk. So I want to just dive right into the library and see what it can do for you, what it actually does. And we're going to do that by exploring how to test a timeout that is implemented using coroutines. So I'm going to make this fairly simple suspend function. It's a suspend function. It's going to load some data, and then it's going to time out 5 seconds later if the API.fetch doesn't return in that 5-second window. And we're going to talk about how to test this thing, and we're going to walk through kind of what's going on under the hood to see how you can think about using this library to test code. So when I want to write a test for this, the first thing I might do is just write a normal test case. This is a regular function, and I try to call load data. And this is, it's not going to compile. It's going to give me an error saying that a suspend function must be called from inside of a coroutine. So I'm going to have to do something to get a coroutine context and start a coroutine here. And I have a couple options, but in KotlinX coroutines test, I can use run blocking test to do that. And this is a coroutine builder. It's very similar to async or launch. It's also similar to run blocking. This one changes the behavior compared to run blocking in a way that's helpful when we're writing test code. So run blocking test basically does two things that are really, really useful when writing coroutines test. It allows you to control the time, the virtual time of the test, as well as it blocks the thread that you called it on. This turns out to be really important because what we want to do is block the JUnit thread that called run blocking test until the coroutine is complete. And I do want to put a pretty large disclaimer on this one. This API is experimental, and it may merge with run blocking before the stable release. A lot of the APIs will end up similar, but the actual function name might change. So now that I'm using run blocking test, I try to run the test, and it's going to fail because I don't know where that string is supposed to be coming from. So I need to do something that I have to do kind of every kind of testing. I'm going to have to introduce some sort of fake or mock version of my API. I'm going to use fakes throughout this talk, but I could do this particular one using mock-k or mockito as well. So I'm going to make a class fake API. It extends API, and all it does is implement that suspend function and just return a string. All right, so this is pretty typical, kind of a test fake that's going to make the behavior go away, so I can actually write a test for it. So in order to use that, I have to inject that into my code under test somehow. And I'm just going to use parameter injection like this. You could take this further if you had a class and put it on the class. You could use a dependency injection framework like Dagger 2 or something else to inject this into your code as well. Now that I have the injection point, I can go ahead and make that fake API and pass it into load data. When I do that, now I'm going to get that result Kotlin, and I can run this test, and I get a success, right? So this is the success path. So this gets us through returning a single result. Now I want to do the thing where I want to test the timeout. So how do I do that? So the thing I really want to do here is suspend API.fetch for 5 seconds. And this is kind of like a core thing that when you're testing coroutines, you really need to think through the suspend and resume behavior as a thing that you're literally working with. So what I want to do is make API.fetch suspend the coroutine until the timeout coroutine wakes up and cancels the API fetch. So in order to do that, I'm going to make a different fake API. I'm going to make a suspending fake API, and I'm going to reach into KotlinX coroutines and grab a completable deferred. This is basically the same thing as a regular deferred. It's a thing that, like the result you get from async, where you can call await on it. But this one's a little bit different because you can call complete on it, which causes the deferred to be completed. This is a really, 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 really helpful tool when you're writing tests because it lets us do things like what we're trying to do here, where we want to force something else to suspend. But we still want to have control over when it resumes. So I can use that down below in this suspend fetch function. And I can just say deferred.await. So now when the caller calls API.fetch, it's going to suspend, and my test is taking control over when it resumes. So now that I have that, I can go ahead and make it up in my test. And I go ahead and call load data with this new API. And when that happens, this API.fetch over there is going to get suspended forever. So if I run this, it's actually going to be a correct timeout test already, because run blocking test will auto-advance virtual time. And we'll talk a little bit about how this actually works in just a little bit. But one of the kind of easiest ways to think about this is run blocking test implements virtual time so that it behaves just like real time, but faster. So if you wrote the same test using run blocking and you waited 5 seconds for that timeout to trigger, the same behavior, the same execution order is going to happen with run blocking test. So this is kind of like the real key to understanding auto-advancing of time, is that the auto-advancement of time behaves exactly like wall clock time. So if I do that, it throws an exception, which fails this particular test. But if I make it expect that exception and run it again, it's going to go ahead and pass the test. So we've implemented a complete timeout test here, and we've covered a couple different things that we might do while testing coroutines. So let's dive in quite a little bit further into this fairly simple code and fairly simple coroutine test and see what's actually happening here. So when I call run blocking test here, I'm on some testing thread somewhere, and run blocking test is going to block that testing thread. And then it's going to make a new coroutine. Because remember, it's a coroutine builder. So it's going to make a new coroutine just like run blocking, or just like async, or just like launch. And I'm going to call that the test coroutine. And that's what runs this lambda in here. So then the lambda continues, and it's going to block the main thread for the entire duration of that coroutine. Then I'm going to go over and call with timeout up here. And when I call with timeout, that's actually implemented by making yet another coroutine. There's a lot of coroutines when you write coroutines-based code. So with timeout is going to make another coroutine that's going to schedule itself to execute that timeout 5 seconds in the future. Then it's going to call API.fetch. And then at this point, all of the coroutines that run blocking test knows about are suspended. So at this point, it kind of gets to the situation where it's like, I wonder if advancing time would cause one of these coroutines to wake up so that I can complete this test. The other option that it could take is at this point it could fail the test because all of the coroutines are suspended. But it turns out that's a less fun way to write tests. So all coroutines are suspended, try advancing time, and then 5 seconds later, that with timeout resumes itself, cancels the job, and that's going to throw that exception all the way back out, and we're going to get that exception over in run blocking test. So this sequence diagram here has a lot of different moving parts, but the key is that there's this thread on the left that's been blocked by run blocking test, and then I create a whole bunch of different coroutines, and run blocking test waits for all of those coroutines to complete before run blocking test is done. If all of the coroutines that run blocking test knows about get suspended, run blocking test will advance time to see if any of them will wake up and continue the test. A really, really important thing to kind of remember as you're using this library is when you use run blocking test in this way, all of this executes on a single thread. So I'm still getting concurrency from coroutines, but I've taken this code right here, and I'm executing all of these different coroutines on one thread. So if you look at this diagram, you might think this is 3 different threads of execution, but really this is 3 different coroutines, all jumping between each other on one thread. And you can see which coroutine is currently active on that thread by the solid lines that I drew there. So at the beginning, it jumps over to the test coroutine, and then over to the with timeout coroutine. Everything suspends for a while, then the timeout coroutine resumes, and then passes control back. So this is kind of a key to understanding, when you get down to this level of coroutines, what are you thinking about when you're writing a test for them? So let's go back to this code here. And you might be thinking, I've tested correctly that some timeout is implemented here. But if I just advance time until I find some coroutine that wakes up, I haven't tested that there's a 5-second timeout. There could be a 5-hour timeout in there, and this test would pass all the same, and there's no assertions that that's happening. So inside of my run blocking test lambda, I get a test coroutine scope, and this gives me a nice API for controlling virtual time. So here I can say advance time by 5 seconds, and this is going to push that virtual time forward by 5 seconds. And then I can use that deferred.complete in order to actually resume that API.fetch that's suspended over on the other side. And if you kind of think about how this works, the timeout should have triggered prior to me doing this deferred thing here. So even though I'm resuming the API.fetch, that timeout should already have thrown an exception. And if you run the test, that's actually what happens. The timeout here happens because that happens right away because of that same behavior we had before. And then the lines below are actually never reached. So instead of that, what we can do is we can actually launch a new coroutine inside of our test. And this kind of so we're just going to add more coroutines to our coroutines test, and that's going to make things better. But what we're going to do here is we're going to make a coroutine just for handling load data, and it's responsible for taking care of load data, and then control jumps right back to the run blocking test lambda right away. And this is kind of a trick to think about as you're kind of building more complex concurrency. And this sort of pattern comes up all the time when you're writing test cases for coroutines. So now that I do that, I can run the test again. And that exception gets thrown into that launch job. And then down below, I get all the way to completion before the test passes. So now I have a correct test. And if I change this out for 6 seconds here, we'll see that this test will, in fact, fail. So this is one of my rules when I'm writing coroutines test. When I find myself in a situation where I can't quite figure out how to get the coroutines I currently have to do what I want, I ask myself, can I add more coroutines somewhere in order to make my test a little bit more asynchronous so I can get multiple threads of control jumping between each other. So I want to transition from that first test and talk a little bit about what's in the library. So what's actually in Kotlin's coroutines test. And a huge disclaimer, this is all experimental. It may change before stable, but this is out now, so you can play with all of these things and use all these to write tests today. So there's basically 4 big things that are going on in the the Kotlin coroutines test library. There's run blocking test, which uses test coroutine scope in order to implement all of that time control stuff. And then test coroutine scope has a test coroutine dispatcher as well as a test coroutine exception handler. And we'll kind of walk through each of those in turn. But the kind of things that you should really be thinking about is the 3 that are very important are run blocking test coroutine scope, and test coroutine dispatcher. So run blocking test, it makes you a new test coroutine. It's a coroutine builder, just like async launch or run blocking. And it gives you that virtual time control. And it has some cleanup assertions to make sure that your test was sane and didn't do anything that's going to leak into the next test. Test coroutine scope, just like a normal coroutine scope, is the thing that keeps track of all your coroutines. And it also has some cleanup code to make sure your test is sane. So then test coroutine dispatcher is the important one. That's actually the thing that actually does all of this virtual time control. If you've used RxJava before, this is very similar to a test scheduler in RxJava. And then there's a test coroutine exception handler. You'll probably never type this line of code ever. This thing literally just tries to catch uncaught exceptions and rethrow them into your test body. So the important ones here are run blocking, test coroutine scope, and sometimes test coroutine dispatcher. So in order to write tests in a larger context, you very often have to inject a scope or dispatcher into the test that you're writing, or into the code under test. So this is one of the keys to kind of thinking about how to write a test using run blocking test, because it really only works if you do. If you don't do this, you're going to switch to another dispatcher, and in a lot of situations, that's going to lead to a situation where you don't actually get the result that you want in your test. So let's take a look at this relatively common code. This is very common, especially in UI code on Android. So I'm in response to some event. I'm going to call this function, and it's going to launch a new coroutine. And then inside there, it's just going to call that API.fetch. So if I want to test this, and I use run blocking test, what I can do is call load data. And then the question becomes, when does that next line of code run? And the answer to that is complicated and not reliable. So what's actually happening here? We'll go back to another sequence diagram like we had before. So run blocking test makes a test coroutine, and then that's going to go ahead and call load data. And then at that point, the application scope creates a new coroutine, but run blocking test doesn't know anything about it because you didn't share a scope or a dispatcher. So at this point, to which order these things run in is kind of unknown. You really don't know which one's going to happen first. So run blocking test, because it doesn't see anything, is actually going to complete right here. And then that coroutine that we launched is just going to go ahead and kind of like hang out forever, or hang out until it completes on its own. So this test right here isn't going to be able to like deal with the fact that load data happened unless I do something else to synchronize between these two things. What I can do instead is make a new application scope over in my test code over here. So I'm going to use test coroutine scope here, which is the coroutine scope that run blocking test uses. And then I'll use some form of injection. I'm going to either inject that with a parameter like I did before, I'm going to put that into Dagger2, or I'm going to put that into some sort of service locator. But I'm going to make it so that that makes its way over to the code under test. And then inside of my test itself, now I'm going to say application scope.runBlockingTest. So this is going to run the run blocking test lambda on the scope that was created and injected over into the code under test. And this is kind of like really, really important right here, is if I called run blocking test without saying application scope.runBlockingTest, what I'd be doing is making a new coroutine scope, because run blocking test does that for you underneath implicitly if you don't pass it one. So you really want to run an injected scope or dispatcher, and there's two different ways to run blocking test on an injected scope or dispatcher. You have this extension function here, test coroutine dispatcher.runBlockingTest, as well as test coroutine scope.runBlockingTest. And both of these exist because in different test cases, you're going to have either a dispatcher or a scope. It's common in Android unit tests to only have a dispatcher. In other situations, you may have a scope. So now when I run this, because I've injected that application scope, that application scope coroutine is actually using the same coroutine scope as run blocking test. So I get a wire, the test coroutine now knows about the application scope coroutine. So while that's suspended, test can run, and now all of these things know about each other. So application scope coroutine has to complete in order to get over to the completion of the test. So now I have gotten this coroutine back under control of run blocking test. And then at the end, just because I love that flame animation, the last coroutine goes away. All right, so let's do a little Android break right here. Everything else I tried to keep a little bit neutral because we're at KotlinConf. There's Android as well as backend developers here. But in Android, we have this thing, this main dispatcher, dispatchers.main, and the Kotlin X coroutines test library gives you a way to call setMain and resetMain. And this is super important in a unit test on Android because if you develop Android, you know you can't use the main looper from a unit test. And dispatchers.main by default dereferences the main looper. So you'll really want to use this for all of your non-instrumentation tests, all of your unit tests in Android, to mock out the main looper if it's being accessed via dispatchers.main. And you'll want to wrap that up into some sort of JUnit4 rule. This isn't in a library, but if you want to find a good implementation of it, you can check out the Kotlin coroutines in your Android app code lab, which has been recently updated for KotlinConf to have all of the material around run blocking test and test coroutine scope. And it also has an implementation of that JUnit4 rule. All right. So the next thing that I really want to talk about when I'm talking about testing coroutines is diving into event loops. So there's a lot of implicit stuff happening in these sequence diagrams I keep showing. And if you don't understand the event loop that's happening, it could be like maybe these lines could be in different orders. And so one thing that's really, really helpful, I find, when I'm testing coroutines with a library like this, is really kind of thinking through the existence of an event loop. I like to call this like, what is this magic? How does this thing actually work? So as a little bit of like a background, I could talk all day. I could talk for 40 minutes about how cool event loops are. But a little bit of background, but what an event loop is, is really quite simple, and this is like a universal thing. It's in every programming language on every single platform. It's a priority queue and then an infinite loop that reads off that queue and then runs the next action. And then the real trick here is that's an infinite loop, and it's the entire, like it holds some thread, and this loop now owns that thread. So it provides two interfaces. One is dispatch, and the other one is dispatch later with some sort of delay. And if you're an Android developer, this probably looks exactly like the main looper, because it is exactly like the main looper. That is an event loop, for example. When I dispatch, I'm going to schedule something for now, and when I dispatch later, I'm going to schedule it for later. And the real trick to like this is the queue is a time-ordered queue. So if I say I want something in 5 seconds and something in 6 seconds, those will always end up in that order. And it's also a first-in, first-out queue. If I say I want something in 5 seconds and then another thing in 5 seconds, they'll execute in the order that I provided them. And we can bet on that as we're writing tests. So I have this timeout test that I did earlier, and we had this simple version here, and then I kind of made it more complicated, added more coroutines, and I showed you this pattern with completable deferred. And I chose to go with that for the first example because that's a very general pattern, but it's not the only way to write this code. Another way to write this, if I'm just trying to test a timeout, is to go ahead and make a delay fake API, right? So this thing is basically going to use, it wants to do a thing. It wants to suspend for a certain number of milliseconds, and then it wants to resume. And it turns out there's already an API for that, and it's delay. So all I'm going to do is inside of fetch, I'm going to suspend for the past in time, and then return that Kotlin, right? So this is something that is now going to give me that suspend for some amount of time and then resume behavior. And I don't have to code that all up myself. So if I go ahead and use that and give it like 5001 right here, I'm going to get this timed out waiting for 5,000 milliseconds exactly the way that I expect. And so what's going on here? And I think it's important to kind of understand all of the things going on with the event loop to understand this test. So the event loop has this queue, and there's basically it's just keeping track of all the coroutines that are just about to run or should run later. And at the beginning, when run blocking test starts, it creates a new coroutine, and it's going to dispatch a coroutine, the test coroutine, at time equals 0. And this is the virtual time. So that's going to go ahead and run, and it runs through all of this stuff here. There's no suspend points. This isn't actually doing any coroutines work, so we're not actually dispatching anything. We're just running a block of code. And then we go up here, and we get to with timeout. And this is going to dispatch another coroutine at time 5,000. And then we're going to do that delay call, and that's going to dispatch another coroutine at time 5001. So then we do the auto advancement of time, and that's going to run this timeout right here. And then that throws the exception and cancels the delay job. Right, so this is an important thing to get as you start thinking about coroutines, as you start testing concurrency with coroutines, is how the event loop works underneath the hood. And this really comes back to this run blocking test. Implements time faster than real time. It doesn't rely upon the wall clock, but it follows the exact same order as your code would if it was using a wall clock. And if you embrace the power of the queue, you can often make your tests much, much shorter. So then I want to talk about when to use this library versus other ways to write tests. So there's a couple things that you absolutely need to do. So if you're in a unit test on Android, you have to inject main. If you're going to dereference dispatchers.main, your test is going to crash if you don't do this. So you absolutely have to do that. If you need to control time, this is definitely the way to do it. And if you need to test concurrency in a unit test, this is a very, very good way to do it. But as you saw, with the event loop, we're getting a little bit low level. Sometimes, though, when we don't want to use it is if I'm writing a larger integration test that doesn't really care that these things are implemented with coroutines or what the concurrency model is. It just cares that a function gets called, some stuff happens, some side effect happens. If I'm okay using the wall clock, if I don't actually need to mock out time, and if I'm not testing concurrency, maybe I don't need to be using this stuff. So I want to take a look at a test that maybe I wouldn't reach for these libraries. So I'm going to make some observable. I'm going to make like a live data on Android or a flow or my listener because I have my own listener class. And then I'm going to do a load side effect function. So this is going to launch something on a scope. And then it's just going to tell that observable about the result from some API call. So this is relatively common code. On Android, we would do this typically with like a live data, but this is like some relatively common code to launch a coroutine that takes some side effect by using an observable to tell people. If I wanted to test that, I don't really need to care about the fact that this uses coroutines at all. This could be implemented with executor services or RxJava, and the end result is I call that function, and then sometime later a result goes to the observable, and then I just want to check the result that went to the observable. So I don't really need to use any coroutines testing in order to write this test. That said, I might actually choose to write this test using test coroutine dispatcher, because by not using test coroutine dispatcher, I am introducing parallel execution. So now I have one thread that's running the side effect test, or the side effect code under test, and then another thread which is actually running my test. And if I can bring those together, often that makes it a little bit easier to think about stuff. Particularly writing a correct implementation of get or await value is somewhat tricky because the value may have already been emitted before it actually gets to that line of the test. Another place that I would probably just go ahead and use run blocking quite clearly is if I have this function called a lot of code, and it calls large architecture.run everything. And it's going to run like something like 500, 1,000 lines of code, possibly with like all sorts of interesting concurrency stuff in it. So here I might go ahead and write a test that calls run blocking and then just calls a lot of code. And I want to take a step back because I think at the beginning of this talk I talked a lot about like detailed small unit tests. But I've also worked at a lot of places where I walk into a team with like a 100,000 line source code, and then I open up the test folder and there's one test that says example test 1 + 1 = 2 and nothing else. So the first test I write when I start at a job like that is usually something about like this. So while I think that there's some problems with this test, this is probably not my favorite test that I've ever seen. It has parallel execution, it has wall clocks, it might have coroutine leaks, it has uncontrolled execution order, and it's probably testing way too much. These are just the things that came to the top of my head about why I may not write a test like this all of the time. On the other hand, I might write a couple tests like this for very critical integration paths. And I would definitely write this if I was in a code base that didn't have very many tests at all. Because one test is way, way, way better, and it's infinitely more than 0 tests. And you start, if you want to get to like 80% code coverage, you're going to have to start with your first test. And usually, this is where the code is if there's no tests. This is about the only thing you can write. So the last thing I want to talk about is testing flow. And I have, actually a surprising amount of time. Well, I thought I wasn't going to have any time at this section, so I pulled the intro section of flow. So I'll kind of talk a little bit more as we go. So I'm going to take, when I want to test flow, what I really want to do is transform it from an async sequence over to a regular sequence. It just makes it a lot easier in my test code to deal with a list or to deal with a scalar value than it is to deal with a flow itself. So what exactly do I mean by that? So I'm going to make a simple flow here. This is a unit second flow. So what this does is once a second, it's going to spit out unit. I probably wouldn't use this flow by itself, but I might use this in combination with another flow to build a larger system. And I want to write a test for this. And so what this, how this actually executes is when someone observes this flow, when someone calls one of the terminal operators, one of the collect operators, it's going to just create an infinite loop that delays the production coroutine for 1 second, and then resumes it to emit a value, and then wait for the next call for another value. And so that's kind of the behavior we want to be thinking about as we write a test for this, but we probably don't want to be thinking at that level. So in order to write a test for this, what I really want to do is kind of stop this early, right? This is an infinite sequence that I've created. This thing's going to literally run forever. So I can use something like take 2, which says I only want 2 results from this flow. And then, now that I've done that, this flow is now safe to just go ahead and say toList, right? So I can take this thing and I can collect it over into a list. And now I don't have to kind of interact with the asynchronous behaviors of it. I can write an assertion based entirely off of the fact that this is producing a list. And then the simplest thing I might write here is that if I took 2 elements, that the current time of my coroutine test is now 2 seconds. So if I wanted to test it a little bit more than that, often I can't just use take 2. Like that's a nice trick, and when I can get away with it, it really solves a lot of problems. But often what I really need is to get the current values from the flow, and then do some stuff in my test, and then check that some new values were sent to the flow. Right, so this is often what I want to be doing. So in order to do that, this is very similar to when I wrote that timeout test at the very beginning. So what I'm going to do is I'm going to launch a new coroutine, and I'm going to use that to collect this list. And I can provide a destination mutable list to the toList function. So this code right here is going to launch a new coroutine. It's going to store the job from that coroutine. And then as the rest of my test executes, whenever the flow has a new value, it's going to update this list. So I can always look at this list inside of my test, and it will always have the current emitted results from this flow. So now I can go ahead and just advance the time. I can use advance time by 2 seconds. And then I expect that the destination should now have 2 elements in it, right? So I can now write a test based upon the behavior of the flow as I take various actions inside of the system. And now if I run this test as it's written right now, it's going to make my machine very hot and destroy my battery. So this test right here actually is going to go ahead and run an infinite loop. And the reason for that is run blocking test is going to try to auto-advance time, and it's going to wait for this job to get completed because of structured concurrency. And so it's going to be like, wait, this job's not completed. Can I advance time a little bit more? And it's going to emit unit a lot of times, and it's never really going to run into any sort of resource constraints that's going to stop it. So this is just going to use a lot of CPU for a really long time. So in order to fix this, and this is another thing that you have to think about a lot, is these terminal operators on flows that last for an infinite period of time like this, are going to create a coroutine that lasts forever. So in order to fix this test to make it actually run, the way to do that is to cancel that job. So what I want to do here is just go ahead and say, I don't need to run that job anymore because I've already made my assertion. And this is going to clean up the flow production as well as stop the flow collection. So then if I run this test again, I'm going to go ahead and get a successful test, and it's no longer an infinite loop. Okay, so that's what I have for you today. And I want to mention, again, this is all experimental, and a lot of these things are probably going to change before the final thing. The big one is run blocking test and run blocking may end up merging their APIs together. And there's a couple other APIs that we're talking about as well. As you're writing tests of coroutines, there's basically 2 paths to take. One, you can treat them as integration tests and not worry about the fact that the code's written with coroutines. And this is a very successful pattern, and I use it a lot. Or if you're testing the coroutines themselves and actually testing concurrency, very commonly you'll need to think about how you can add more coroutines to your test case in order to get the asynchronous behavior that you want. And then please remember, one test is more than infinite tests. If you walk into a code base or you're currently on a code base that has 0 tests, it's better to write 1 bad test than it is to continue having 0 tests. So thank you so much for coming, and I'll be around for questions, and I'll be working at the Google booth later this afternoon if you want to catch me there.
Oh, I have. Copenhagen. All right, I see people raising their heads up, so that's good. I'm Ana Redmond. I'm the founder and CTO of Infinite. And I build educational games for kids to teach them math concepts in a play-like manner so they not only understand, but enjoy learning math. And today, I'm going to talk about how I took 6 years of that Android game code and ported it to iOS in just 6 months using Kotlin Native. So I started building these educational games for my daughter when she was in kindergarten, and she was falling behind in math. So how many of you have seen that expression on your kids' faces when it's time to do math? Yep, that's my daughter's. So I found out, and I discovered accidentally, that the reason why my daughter was so frustrated with math learning was because she was being taught to memorize math instead of understand it. And I'm an engineer, you're all engineers here, so you all know it's not about memorizing or rote memorization. Math is about understanding and applying it to the real world. So that's when I started building her games to do exactly that. So addition was 2 + 2 was put 2 items in a box and then add 2 more. Or subtraction was put 4 in the box and take out 2. And that worked really, really well. She not only started to understand the math, she was really actually started to enjoy it. And I had about 1.5 million downloads of those early prototypes. And as she grew, I started building more games for her. But these were onesie-twosie games that I built as and when I could for several years. Then in early 2016, we were awarded a National Science Foundation grant. And with that grant, I put together a team, 2 engineers, including myself, a graphic artist, an audio engineer, and a curriculum designer, and researcher. And we built 120 math lessons, all through game-based, play-like learning, 60+ games that taught kids from kindergarten through 2nd grade all the concepts that they needed to know in their math curriculum, step by step. One of the key aspects of the games was an integrated audio and visual feedback when the kids make a mistake. So play-like learning is fundamentally about making mistakes, learning from them, and then building a conceptual model by getting the feedback on what type of mistake you made. And it's really, really effective for learning. It's way past the reported numbers for pretty much any other software for math learning available today for kids. So end of 2017, we were Android only. And it had taken us 6 years to get to 60+ games at that point. This was all built in Android native using Java at this point. And people kept asking me, when would it be available on iOS? Or, more often the question was, can I play it on my iPad? And it's like, no, sorry. But I had this idea soon after Kotlin Native was announced that I could potentially build a very thin game SDK layer for both Android and iOS, and then build all my games on top of it and make it available on both platforms. Sorry, my bad. And make it available on both platforms, going from, for Android, just doing Kotlin, and on iOS, doing Kotlin Native, and building an iOS executable through that. But the idea was that all these learning games with feedback and all that complex logic, that we would only have once, and would only need to maintain it once. And that was really a big thing. So I applied, actually this diagram is from a grant that I applied for in December of 2017. I applied for a grant with the NSF. That grant was actually rejected. And the feedback was something like, not enough technical detail, which was fair enough. I actually had no idea whether this would work at that time. I had not done any proof of concept or prototyping or anything like that. But I spent a couple of months trying to find funding for it, and I couldn't. But I said, whatever. It's like, I'm just going to go ahead and try it at least and see whether it works. Like, I'm not being very convincing about this working yet. I feel like I'm losing my mic. It's flowing backwards, sorry. And the result was that in 6 months, I had ported all of the 80,000+ lines of code to iOS and published all 3 grades to iOS by December 2018. With the last release that just went out in November, it's also completely free for teachers, for students, for parents. No ads, no purchases, nothing. So all your kids can use it, enjoy it. Please send me feedback if you do use it. So let me show a demo. I'm running this presentation from an iPad. So I'm going to show the first grade, live demo, prayer to the demo gods. So this is the starting screen. Teachers can define multiple profiles for their students, and they can play through that. There's tracking. There's assignments. They can assign different lessons to the students. The screens I've shown so far, these are all actually in native. So we didn't try to move some of the starting screens or the introduction screens into Kotlin Native, but we moved all of the game screens to Kotlin Native, and they are shared code through Kotlin Native. Let me show the demo, and then later I'll talk about how we did that.
Hang clothes on the number line to complete the sequence.
So let me do a mistake.
6 minus 2 minus 3 is not 4. Keep trying.
So now they get this, they get some feedback about why they did something wrong, and then they can sort of use the same methodology, 1, 2, 3, 4 in 1, so it must be this one, to actually complete the exercise. This feedback is the core of where learning happens. But this feedback is also really hard part of building these games. Let me show a more complex example. Compose 10.
Put 9 plus 1 cubes on the grids. Compose 10 ones into a 10. Add 20 plus 10 cubes. Read the place value grids to find the answer.
I'm going to deliberately make a mistake.
9 plus 1 equals 10 plus 0. 10 plus 20 plus 10 equals 40. 40 is not 30. Try again.
So all of these animations, everything that you see on this screen is actually built using Kotlin Native or Kotlin Common Native. I'm going to clarify those terms in a sec. All of the stuff, the buttons are just 2 images for different states, something that happens when you press it. All this motion, when I touch the screen, something happens. All of the animations, it's all built with Kotlin Native. I'm just going to show this last one. This is a fun one that the kids really like.
Feed the monkey 1/2 of the pie. That's 1 out of 2 equal pieces. Press the number 1/2 when done.
Oh, that's a system sound. It doesn't go through HDMI. It says, I'm hungry. So whenever the kids are playing it, we can tell they're playing it. They have headphones on, and they're just talking about, I'm hungry. Bye. Right, so let me go back to the presentation. So that's the demo. The profile, the tracking assignments, those are not in Kotlin Native, but all the games, all 60 plus of them, are in Kotlin Native. So let me clarify some terminology, because I was also getting confused when I talked about this stuff. Native code is the code that's written in Swift or Objective-C, just like you normally write native code, and or in Kotlin or Java in Android. Could be either Kotlin or Java. Kotlin native code is code that's written in Kotlin and runs natively on iOS and Android. It compiles down to the executable. And it could be platform-specific implementations. That's, you could have two different implementations for iOS and Android if they are accessing public, the libraries, the native libraries. And common or shared code is code that runs on both platforms. It runs natively, but it's shared code. You only write it once. So why did I decide on Kotlin Native for infinite math? So we had a large number of 2D native games, and they shared a good amount of, with using Kotlin Native, at least I thought I'd be able to share a good amount of code and the feedback logic, and that's how it worked out in the end. And we had very few external dependencies, so not having a lot of the libraries ported to Kotlin Native was not a big deal. And whenever we couldn't do something in Kotlin Native, we could just simply go back to native and just do it twice in that. It was really about minimizing doing that, but trying to reuse as much of the code as possible. So this is the architecture of the overall apps. So there's 3 published in iOS, 3 in Android, and the lower level here, this is all the libs. So the data model and API, we use Firebase, and Firebase does not have a Kotlin Native SDK yet, so just decided to use it coded in native. Big reason for that was we wanted the caching and the offline capability. That's in Firebase. That's through the Firebase SDK. If you go to the REST API, you kind of lose that. And then the Android, the screens, some of the screens are still in native Android or native iOS. But the big part of it is this, which is all the games are multi-platform, and that's all shared. In-app subscriptions is gone now. We're not doing that anymore, but that was also specific to the app stores. So this is the mapping of the 2D API. These are on the left side, on the common, you see all the functionality that we needed to have available, so then we could build the games on top of that. And if you see, it shows what we need, how it mapped in Android and how it mapped on iOS. It's pretty similar, and there's not a whole lot of it. So it made it really easy, because we're going one layer lower than the UI widget layer. So we're using the 2D API. We're not using UI widgets, which is a much bigger layer. So 2 ways we shared this code in Kotlin Native. Most of it was using expecs and actual, especially most of the functions that we wrapped for 2D API. And the other one where we couldn't use that, we used interfaces, which we defined in Kotlin Common, and then implemented in the platform-specific implementation. I think these 2 are very common if you guys have attended any of the other talks. Everybody's talked about what they are. But I'm going to show you some examples from the code that we did, so you can see what it looks like in a production app. So for expecs and actual implementing something using expecs and actual, we define what we expect. we define what we expect in the common SDK, and then implement it using Kotlin Native in iOS and Android. On iOS, it accesses iOS libraries in Objective-C, and on Android, it accesses Android libraries in Java or Kotlin. And then all the games and all the logic, where you put what image, how does it move, all that stuff is all in multi-platform, and that's shared code. So I'm going to show the example for how we used expects and actual using this game. This was a puzzle game where the kids move shapes around and match them into the puzzle and fill out the puzzle. I'm going to show you that specific heart shape, how we built that. So all the shapes are actually drawn on the screen. They're not images. So that's just for resolution. So in the common game SDK, we define a path display, what we expect or want from a path display. You started something, and you define these functions to create the curves. And you can see here, for example, the first one is drawing a line from here to here using these two control points, so that curve sort of gets pulled up. So it ends up with that curve, and so on. So it's using the cube2, quad2 functions that we defined to build this heart shape. And then the implementation of those is done in actual classes on both Android and iOS. So left-hand side is Android implementation, and you notice that it's using the Android graphics API. And the right-hand side is iOS implementation, which first uses C interop to access Objective-C, and then it uses the UI kit to actually access UI Bezier path. So implementation on Android is path, and implementation on iOS is using UI Bezier path. And then all the functions kind of follow. You see the names are different, the parameters, you have to adjust the parameters based on whatever the platform expects, but it kind of just is simple. It kind of just maps. And this is the implementation of the draw function. This is showing how you draw the stroke around the path. Filling in a color would be very similar as well. So both platforms, easy to implement. The thing I want to point out here is when we are creating this path display function, we're just creating it like a normal class through our common Kotlin code. There's nothing special about it. It's not like we have to do a prototype or we have to figure out what type it is. So using expects and actual, the switch happens at build time. Which implementation it picks up is done at build time. It's not done at runtime. Whereas if you're using interface and implementation, that switch is happening at runtime. So very similarly, this is image load, how to do image loading on Android and iOS, and using, again, expects and actual. This is the actual implementation, but it does get a little bit more complicated at times, but very doable. There is how to draw the images, transform. We also use it for drawing text and for playing audio instructions. So that's the expects and actual. It's just a handful of functions that you have to do with that, and then you can build all of it in Kotlin. So the other way we implement some of the stuff is by using an interface. And we define the interface in common. We implement it in the app using Swift or Kotlin. And then we use it in the game and logic by providing by passing in the actual implementation to wherever it's needed in the games. So I'm going to show the example from this game. Actually, all the games have this. This is the back button. So when that back button, it's not actually a button. It's not a UI widget button. It's two images overlapping, two images that you use. When you press it, it's a different image, and then, when you touch up, then it's supposed to do a back functionality. But back functionality, to execute that, it needs to go back up to the view or the activity in Android and finish that, so all the resources are collected. Or in iOS, it needs to go back up to the controller and say, dismiss this view, and you want all the proper animations to happen as well. So let me first talk about how all the games are rendered. I'm just going to give a brief overview. I did a talk in DroidCon New York, and I have a link to that at the end. You can watch that about how we do these games using Surface View. So on Android, we use a Surface View, which runs on a separate thread. All the rendering is actually outside of the main thread. That's kind of special about Surface View. But how you're doing the rendering is you establish an update and present loop. So it's constantly going through a loop and rendering the screen. So what that means is you can change what happens over time. So Surface View takes control, starts a thread, and just does updates and present on the game. And this is all double buffered, so you don't see any glitches. On iOS, it's very similar, except the functionality is split between screen view controller and the view and the view controller. So the presentation part of it is the view, and the controller part is doing the update and just calling draw on the view. And then the game takes over at that point and just does all of the rendering. So the interface we define for the back function, let me go back to that one actually. So now we want to go from the game. When the user touches the back button, I want to actually call back to the controller and say, go back. So that's where I need to be able to define an interface. Because on Android and iOS, these are different classes. So referencing them back from common, I need an interface. So I'm just going to call it on the interface. So that's the interface, and I define the back function on the interface. That's the function that the game calls when it needs to do something. So here it is, back button. You press the touch up on the back button, and then we go call player.back. So that's how it's getting used. I'm going to point out here, and we'll talk more about this later, this is a weak reference. This is required for iOS. I'll show why. So on the Android side, we implement the game player on the view, and on the iOS side, there's the game player on the view, and on the iOS side, we implement the game player on the controller. And then on the view itself, the context is a function called on the activity, and the activity will, the back pressed, it'll eventually call finish. And on iOS, it calls it dismiss to get rid of that screen. And when to use this in the game, it has to pass a reference to itself when it's creating the game. So it's the this reference on iOS, and here it's passing a reference to the player, which the player is actually the controller at the time the game is created. So now the game has a reference, and it can call the back functionality when the user touches up on the home button or back button. So that works fine on iOS, but on Android, but on iOS, you have to be a little careful. We were getting this memory leak, and it was leaking massive amounts of memory. The controller has a reference to the view, and we just provided a reference to the player, this reference back to the player, which actually creates a cycle. So the view has a reference to the game, so it can update and present, keep rendering it. But the game also has a reference back now to the controller, and that reference has to be weak. Otherwise, you're going to get a memory leak. Now, Kotlin Native has a cycle detector, but that does not work across the boundary of objects that it's managing or not managing, right? So the controller and the view is not something it's managing, so they're only reference counted. They're not detecting cycles. Within this side of it, if there's a whole bunch of cycles, it doesn't matter. It's like it'll collect it eventually. It's better to use the weak references. You do notice a time lag if you try it on the profiler in iOS. And then this weak ref class is a wrapper at this point. I'm not sure if they have released a common version of it. I just wrote a wrapper. There was separate ones available in Kotlin Native, and in Android there's a weak reference class available, but they weren't the same API. It's possible they're going to provide that, or they may already have done that. I didn't go back and look. So we use this same methodology, common interface defined and then implemented back in native, and then you provide a hook for it to call that function. We use this for touch events. We use it for invoking Firebase from the common code and for accessing application scoped objects. So I'll talk a little bit about that in a little bit. But that's my recap. So there's two ways of sharing the code. We can share it using interface and implementation by going up the stream, or we can share it using expecs and actual going down the stream. So which one do you want to use when is the question that I think usually comes up. And it depends on the scenario. I personally prefer to use expecs and actual wherever I can, just because it's simpler and I don't have to worry about the memory, and it's all contained within Kotlin Native. But it can be difficult at times too, because you cannot invoke Swift from Kotlin Native. You can only invoke Objective-C APIs from Kotlin Native so far. So it can become a little more complicated in terms of how you define the types, how you use them. Interop.md was my friend for several months. But there's always the fallback option. If something doesn't work with expecs and actual, the fallback option is always there, where you can go ahead and define an interface and then do the implementation in the app and then pass a reference to the implementation somehow. Yay, they do get along. They're not all. Sorry. Oh, the other thing I was going to mention is using this method, I was able to share more than 80% of the code in the application for iOS and Android. So I don't think that would have been possible without Kotlin Native. I have not seen anything else that I could use to do that. People say, why didn't you build the game in Unity? And Unity is good for single games, like one-off games. But when you're building a library of 60+ games and you want to be able to pull whichever game, it's not really very suitable for that. You just run into too many memory issues. It uses a lot of battery as well. With Unity, we were able to optimize it to use very low battery. And teachers really, really wanted that, because in the classroom, they need their tablet to last for the whole day. So there's reasons why it doesn't work in Unity, and in the standard kind of game frameworks that you might be familiar with, education is a little bit different. Okay, I'm going to go through a couple of lessons I learned as we were building this. One was don't use objects. Object, the singleton type in Kotlin. I think I probably shouldn't have used it anyway. Was being lazy. But with Kotlin Native, it really is just not a good idea. Unless it's like a very complete, enums are okay. Enums are good because they're completely immutable. So, but if it's a singleton and you want to mutate it, that's a no-no. It'll not work because of all the threading issues within Kotlin Native. So this was a class that we were using. Sound Manager was a class that we were using to do these, system sounds, small, short, bursty sounds within the games that, for example, play a chime sound and play the monkey laughing or something like that. I'd initially done it as a singleton because it was just convenient, right? It's like, oh, soundmanager.getInstance.play whatever I needed to play, and it's all over the code. But, sorry, it didn't work when we got to Kotlin Native because of threading. So we were loading these sounds on an as-needed basis, so this object was not immutable. So it's constantly changing, and it's getting accessed on multiple threads in iOS. So we started getting the dreaded, what do you call it? Like, you need to freeze this object before using kind of exception. And the only solution I found for that was to do it as an application scoped object on both iOS and Android. So I still needed only one copy of this object, but I didn't want to use a singleton anymore. I just put it in the application scope and created one copy of it and then passed it to the games using the game player as before. And then this is the clothesline number game that was in the demo. And here I can just get the sound manager from the player, and then I can play whatever sound based on, at whatever time I need it to. So yeah, don't use objects. The second lesson was arrays versus lists. Swift, I found, does not have the concept of an array. And an array in Swift is actually a list, just to make things really confusing. Yeah, that was fun. So when I defined an array as a parameter in the interface in Kotlin Native and tried to implement that in Swift, or try to invoke that in Swift, trying to pass a particular type of object, and that was array, I got this weird, standard lib array, define the size int, because this was how we were initializing the array in Swift, if it was defined as an array in Kotlin Native. And this is really confusing to read. But so long as you just change that array to list, and then within Kotlin, the functionality is the same. You can just kind of go change it to list, and it doesn't make much of a difference. In that case, I could just use the standard array format in Swift to initialize the objects. So I was like, don't use arrays in Kotlin at the boundary of where it needs to talk to Swift. And the third one was this very weird one that I'm not entirely sure is a bug or not. The initialization order. So if you have a parent class and you call an init function that is overridden in the child class, then this variable that is defined in the child class, this variable, it will have different value on iOS and in Swift, or in iOS versus on Android, even though it's the same code. It'll have different value on the two different platforms. Turns out on Android, it works as you would expect it in Java, which is like you declare first and then you initialize. It looks like on iOS, it's doing the reverse. It ends up initializing first and then declaring it, which is very weird. So I'm not sure how it's implemented in Kotlin Native. This pattern was, I think, an artifact of the fact that we didn't have an init block in Java. So we were trying to do this thing where we would create, and we created our own function init child and tried to override that in the subclass. So the solution for this is to move that variable, the easy solution, the hacky solution. Preferably, you should clean it up, but the hacky solution is to move that variable into the parent class, and then everything initializes correctly. It's only if that variable is in the child class that it's confused, that it has the wrong value. There's a couple of links for you if you want to see how or why we did use Surface View to build these games. And then there's a 12-part series on all this porting, from going from the beginning to doing the build, setting up the builds, all the way down to production, that I wrote as I was building and doing this stuff. So it may be a little bit out of date, but if you want to know the background. And then I was going to add this to my own Medium account, but apparently JetBrains is going to publish the talk. So thank you so much for coming in, and please remember to vote. And I'll be here for questions after the talk.
hello.
Hello. Oh, working. Yay.
Hi, everyone. My name is Mike Nakhimovich. I'm an Android engineer at Dropbox.
And my name is Yiğit Boyar. I work in the Android team at Google.
And today, we're here to talk to you about a library called Store that we've had a delightful time converting from RxJava to Kotlin and Coroutines. Anyone that knows us knows that we absolutely love Android. And really, what we love is how easy Android is. Primarily, working with data on Android is easier than it's ever been. We stand on the shoulders of giants. Really not giants, but giant libraries. When we fetch data, we don't have to go to low-level primitives like HTTP URL connection. We can use high-level libraries like Retrofit or Firebase to do our networking for us. Similar for caching. We have solutions from Jetpack like Room, things from Square like SQLite, or even if you're working with files, you can use OKIO. And my favorite, transmitting data in a reactive fashion, we have plenty of options. RxJava started the trend. The Android team gave us live data, and now we have flow coming from Kotlin Coroutines. The thing I get asked a lot is, how do we put it all together? How do we put all these great libraries together into an application? Recently, the Jetpack team has been doing an incredible job giving us guidance of how we should build applications. And this is one I really enjoy, the Guide to App Architecture. I like it because it has this beautiful diagram of how you should architect your Android application. You start with a fragment and activity, which talks to your view model that emits live data. The view model communicates with a repository, and your repository is owning the local source, something like a database, and your remote source, something like a networking client. So let's take a look at what the Android ecosystem gives us to have as implementations for all of these recommendations. We all know fragments and activities. They're in Jetpack. Similar for view models. You don't have to build your own. You can use the Android X, the Jetpack version of it. Local sources, we have Room, which is an ORM that can wrap SQLite, the base implementation for databases. And our remote, even though we don't have a great network client in Android, Square made Retrofit, and we've all kind of settled on that as the de facto network client that we use. And then we have this. They give you a few samples, a few examples of code snippets, but really, they just tell you to figure it out yourself. Thank you for that.
No problem.
So, this is a pattern. This is a problem that is really dear to both of us. It's something that we've both tried to solve on our own. And we thought, why don't we this time try to approach it and solve it together? So before we do that, let's figure out what the problem is that we're trying to solve and what previous solutions or tries of mine, how far they got. The repository pattern was defined by Microsoft's architecture documentations as the class or component that encapsulates the logic that is actually getting your data from what the components that are then using your data. This allows you to centralize the logic for managing your data. You don't have to have parsing logic living in your views or your view models. It can all be in a centralized repository that many UI components use. It removes that burden of having to do logic or having to do fetching within your UI code. And that enables us to build reactive, data-driven UIs with very thin clients that are just reacting to new data as it's flowing through our reactive streams. So this was me many years ago. I looked great. I'll be the first one to say it. And this was me at DroidCon Italy premiering a library called Store that we developed at New York Times. We had a data loading problem at the New York Times where we loaded a lot of data. And one of the table stakes for us was sharing our responses. So let me give you an example. When our app opened up, we had a view pager with many fragments, each for a different news section. And they all needed a config object that came from a config API. Right now, what they did before we had Store was make 4 of the same requests to Retrofit, which will make 4 requests to the backend. Same request, same response, expensive parsing in there, and it's returning a little too much money from your users' wallets. And we kind of wanted to solve that problem, solve that thunder and herd problem. The Times was also one of the first companies to start using RxJava. We loved this declarative way to build our data flows. What we didn't love was the amount of operators that went into building store. We thought it was going to be simple, and it wasn't. So we wanted some amount of abstraction so that we don't have to have every new engineer learning each and every one of these operators, what to do in success cases, how to handle errors, how to do side effects to other components. So we wanted store to be this abstraction that has easy APIs. The way we used store was by building stores that were wrappers around some network client. You would pass it a key, in this case an article ID, and it would return to you a single of whatever the response is. So once you open your store, you can then start making requests to it. You can make a fresh request, passing your key, subscribe to the result, just like any other observable. The only difference between what we were doing with store and what we were doing with just the network clients is that when you fetch the data from the network, we were saving it to a memory cache and then returning it to the user. We were doing this because the other type of request we had was called a GET request. Different verb, same general shape of how you work with it. Here, the GET request, as you can imagine, will just get the data. So if you have it in cache, from any GET request or any fresh request, you will be returning that, otherwise falling to the network, and then going back up, saving your data to your cache, and returning it to the user. And this worked really great for us, so we continued to iterate on it and start building offline stores. Little more complicated builder, but same general pattern. Here, we just pass in a persistor, which knows how to read and write to files is what we were doing, and a naive parser implementation. Once we open the store, our flow starts looking like this. And TLDR, it's just super complicated, and it's, again, not something that I want to do every time I want to build a screen. What store gave us is consistent APIs for all of our requests. We had GET, if I just wanted the data and didn't care if it came from cache, and FRESH for something like a pull or refresh, where you actually want to get network data. So fast forward 3 years, and store is starting to show some of its age. It was great. It was cutting edge at the time. It used Rx, but it was kind of using Rx singles, where we were returning only single responses from the network. And eventually, users and consumers outside of the Times wanted us to have observable streams as well. We bolted it on by side effecting through streams called published subjects, but it wasn't truly reactive, where we can work with observable fetchers or observable databases. So now I'm going to hand it off to Yiğit, that's going to introduce what we've been working on.
Thank you. So today, we would like to introduce Store 4, the next generation store library. It is 100% in Kotlin now. We rewrote the whole library. There is no RxJava dependency anymore. We are using coroutines and flow. It supports observable data sources from scratch by default. Either it's your network or your fetcher, so you can use these things like Room or something like a Firebase backend. And most of this is possible thanks to the nice API we get from using Kotlin Coroutines and Flow. But you might ask, why did we go with Coroutines? We could obviously implement this using RxJava as well. And of course, the main reason is we are excited. It's just cool. New technology. Honest answer. But there's also a good engineering reason. There's a couple of them. And the main thing for us was this thing called structured concurrency. Actually, if you have seen Roman's talk earlier, I think he stole our slides. Very similar, the same idea. But when you use RxJava, it's a really good library, super cool. And if you subscribe to something, it returns you a disposable, and the function has this annotation called check return value, which kind of warns you, the thing I'm returning you need to hold on to it, and you're responsible to dispose it. So it's like, it warns you to think about the life cycle of that subscription. So it's cool. But in Coroutines, this is like the next level, where Coroutines makes you think about it from scratch, because the only way to launch a coroutine is a coroutine scope. So without a scope, you can't even start the coroutine. So you need to upfront think about this thing. And very nicely, most of the time when you need a scope, you need it around you. Like if you're an Android developer and you're in an activity, you want to do something in that scope, there's a lifecycle scope. That's the only scope you have available right there. You'll just use it, and it will work, and it's very explicitly scoped to your lifecycle. So we really love that property. That's not the only thing. Another reason is Android X loves coroutine. There's a lot of KTX libraries coming. We're writing Kotlin first things. Room, our persistent solution, supports Flow. Work Manager has a coroutine worker. There's a lot of first-class support. We are even rewriting paging in Kotlin and coroutines. That was the first Kotlin library we have. So there's a lot of investment in Kotlin from the Android and Android X teams. And like Mike and I have this hopeful feature where maybe we don't need to rewrite this code in every single platform all the time, and Kotlin's multi-platform story is quite promising. And if you think about what store does, a repository is almost always about your business logic, so you have very little reason to duplicate it in multiple clients. So, okay, these are the main reasons for like doing store from scratch with Kotlin and Coroutines. So let's look at how this API looks like. Again, same thing, we have a builder. You give it a fetcher, and here, all I'm giving it is a suspend function, and this suspend function returns a value. Even here already, like we are taking advantage of Kotlin's Fluent API. The same function could have been returning a flow of values, so if it is an observable backend, in this one, it's just a single. Now you can optionally provide a persister to persist the data. The read function is just a function that returns a flow, and the write function is just a suspend function. Like these are all like simple primitive coroutine functions that helps we create this beautiful Fluent API. Last but not least, you can provide a caching strategy or disable it, and then build that store. Once we build that store, in store 4, there is one main API, and that's called stream. It's not about get and fresh anymore. It's all about streams. We still have them as convenience, but the main API thinks about the reactive world. You provided a request, and inside this request, you have the key, which key you are trying to get. You have the list of scopes that you want to use, like do you want to use the cache value, do you want to use the disk value, and you can also tell store to refresh the value even if it is available in the cache. And this is another place where Kotlin really helps us, because in store 3, we used to get this bug where people would use a key that's not really unique, like it doesn't implement equals and hash code properly, and they will complain that it doesn't work. In Kotlin, this is a lot simpler because either is a simple key that already works, or we will tell people to use a data class, and it still works. This is where Kotlin, again, helps and shines. And one more thing. So this returns you a flow of store responses, another place where we take advantage of Kotlin, because this store response is a sealed class. It might be loading. This is going to tell you where the loading event is coming from, like your network is loading. It might be data, in which case it will have the value. It will, again, tell you where the value is coming from. And it might be an error where we have the exception. One important thing here is that we don't throw the exception. So if your network receives an I/O error, we don't throw it. We wrap it in a data class in this store response and give it to you as an error, which allows your UI to be still observing your database for any other changes while also knowing about the error. OK, so let's go through some use cases and how store works.
So the first use case, what I consider the most common use case of how I work with data, is I want data, and I want updates if that data changes. Like Yiğit said, we'll build a store from an API, passing it a persister, a writer, and then build it. We then are able to call, so he said we had a single API. I like convenience functions and making things easy, so we have a few helper functions. Store.get is a stream that will get us our data from whatever whatever source is the first one that has that data. So we make our store request. As soon as we make the request, store creates a flow for that consumer. Now, looking at our store, we don't really see any data in here. So what we're going to do is make a request to the network. When we start that request, we'll return one of those store responses that are part of our loading store response up through our flow. Eventually, we get the value from the network. Rather than just returning it, we'll save it to our disk, save it to memory, and then flow out. Great. So you had an app, it's just calling store.get and giving you values as you open whatever your activity or fragment is. Now, someone's been using your app for a while, they navigate to different screens and come back to the screen that we were on. There's no state that you really have to maintain within your UI to allow you to get the data for it again. You, again, will just do store.get, same exact request, but now, since we have data in memory and on disk, when we make our flow, we actually return our cached data back out rather than hitting the network. Same code. UI only holds an identifier. We don't have to persist it or serialize it or do anything else besides just holding our identifiers so that we can access that same data again. All right, you've used the app, you've backgrounded it, and now you're going to use all the other delightful apps on your phone. You come back to the app, and now you don't have anything in memory when you get that same request of your app coming back up. So let's say there was process death in between you using the app and then coming back to that same screen. Now, when you come back in, you have data on disk. You make your store request. We fill memory again so that every request past this one will be quick, and return it from disk. That was the simple, most common case, but a lot of apps actually work similar to what Gmail does, where when you open Gmail, you see your old messages, and then you actually want to refresh and get your new messages as well. So we have some data that was already in memory and on disk. And here, rather than calling store.get with refresh false, I'm calling it with refresh true. And this is where we shine that now we are flows, so we can return multiple values. We'll first return whatever values, if we have them in our cache. We'll then signal that we're going to be loading from the network, make our network request. Oh, we got a new value, 2 instead of 1. So let's update disk, update memory, and return 2. Similar, we can work with a stream, skipping that cache. So when we get that request, we make the flow. We're not going to get values from disk since we did a store.fresh. That's the only difference. I would think this is something like a pull to refresh would have this rather than just a get call. We'll return the loading and go to the network. So fresh makes it always seem as though you do not have something on disk from the perspective of the UI. And that's really the only directive that you really have to think about of, am I getting data or am I getting fresh data? The more complicated stuff that we were unable to do with Store 3 when we were working with just singles is what if we had observable sources? Like now room exists, and we could actually listen for a flow coming out of room. We'll think about this example as a to-do list where you both have data locally and from network. When we make our request, because we're making a store get request, and we already have data locally, we're going to return from that store whatever that data is, just like the other ones. Now, the only difference here is if our database actually gets a new value that gets emitted from whatever that reader flow was, we will, in fact, emit that to the user as well. So you could actually work with both observable databases and observable networks. Let's say one's a WebSocket and the other one is Room, and both of those updates will flow through your store back up to your user. What I love about this is how easy this case is. It's every bit as easy as the simple case is. You're really only changing a verb or some directive, and you're able to interface with your store in the same way that you do with really basic APIs. Now, I say this is simple and easy because I like being a consumer of a library, but there's actually a lot of complexity hidden under here to make source of truth work, and Yiğit's going to do a deep dive on it.
So source of truth is one of the concepts that's like very, very easy to get wrong. I'm going to show a use case here. I'm pretty confident that most of you can relate to this. So I have an application here, let's say it's like Dropbox or Google Drive that lists the folders I have. I hit the plus button, add a new folder for KotlinConf, hit save, it goes back. I'm seeing the loading spinner. I'm not seeing the KotlinConf there, none of it. And only after it finishes loading, I see KotlinConf. This is a horrible user experience. I just saved something on my phone, I have no idea where that folder go. Did it even save? I cannot use it. You don't want to put your users into this state. So what's happening there? What's the problem? We have that first screen that lists all of our folders, and that makes a network request, gets that list, and displays. And then you go to the add screen, which makes another network request, adds the new folder, is done. You go back to the previous screen, makes another network request, gets the updated data, and if everything works, like you are not in a metro or anything, it shows the data. So the problem here is that you are missing a reliable source of truth that's locally accessible. So we want to put this. It's like usually a database, might even be the file, like something you can modify locally and then synchronize to your backend asynchronously. Meanwhile, your UI can be snappy because it's just loading local data. You don't need to rely on network. So when we're trying to design store 4, one of the questions is, should we make this store? Like, should we make store a library which handles all of the persistence of your data plus fetching it and just like a one-stop solution? And really, in terms of API, it boils down to just one single API difference. In store 3, we had this API with the persisters where you could put a value or get a value. Instead, what we wanted to do in store 4 was this. We wanted the local persistence to be able to return a flow. That means it can actually update itself without going through store. Obviously, the advantage of the first implementation we had in store 3 was it was very easy for store. It only had to track what it knows. It never got invalidated by other things. So it was an easy implementation. The flow of code was always one way. But the problem with that solution is that it forces you to rely on store for everything. So if you want to start using store, you have to move everything to store, or it will be inconsistent with the rest of your application. And if you want to do a partial migration, every time you change your code, like you have something that updates the database, you have to inform store. Like, for example, if in my application I had some code that ran a simple SQL query to update some records, you cannot do that anymore if store doesn't support source of truth. You also need to tell store to invalidate some data. And this is just ugly. This is bad developer experience. We said we don't want this. So what we ended up doing, and also like there's one more thing, where when Mike first designed store for like 3-4 years ago, it was a different world. There was no public room, like the observable databases wasn't a common thing. So it was a different world. Today, we have Room, SQLite, RAM. These are all observable data sources. They already do the hard work. Why not just build on top of them? So if you go back to the previous question, we said, no, store shouldn't be your source of truth. Store should just work with your source of truth. You can just think that as your database. That's the most common case. It should work as a mediator between your local storage and network and whatever else you have. And if you look back to if you remember the architecture diagram Mike showed before, this exactly looks like a repository. So kind of, yes, we are in the right space. It looks the same. So when we go with this model, that means it fits the current architecture recommendation. It should be easy for people to migrate to start using store. It allows out-of-bands updates. It's your source of truth. It's your data. You can change it however you want. Store will catch up. It simplifies user code. You don't need to think about managing store, which enables partial migrations. But it's easy to say, nice graphics, Mike, but it's very not easy to implement. So we showed before, every store response comes with an origin. We want to tell you where this data is coming from so you can update your UI properly. Because let's say you want to get a fresh, like you are just getting requests, you want to know if it came from the network or if it came from the local storage to properly update your UI. So in theory, how this works is when we get data from your database, it comes to store, and it just sends it to the downstream flow. We get value from your network, it comes to store. We cannot send it to downstream now, because this will invalidate the source of truth. What if you have a trigger in your database that will update the fields when you insert that record? Like we cannot send the value to the user without giving it to your disk. because it's a single source of truth. That's the whole point behind it. So what we do instead is, when the data comes from the network, we first write it to your database. We know it's observable, it's the API. It will send us an update, but we know it's the update we just gave it, so we change the origin, back the network, and send it to downstream. It can even change the type, which happens very frequently, right? The class you fetch the object from your API endpoint is usually not the same class you use to persist it. So this allows you to control all of that. Now, that wasn't very trivial, actually, when we were writing. And this is another place, like maybe us learning coroutines properly. But the first implementation we had was something like this. Basically, put this item into the store, and then mark the next item as if it's coming from the fetcher, so we can change the origin. But when you do this, this is a suspend function. Actually, we wrote this. It was working fine in practice. But when we tried to write tests, it broke. The problem was this. When you put an item, we are suspended. So we have zero control over the implementation of that source of truth or when it will inform us. It might actually inform the downstream flow while we are writing the item, which means now we don't know that this actually came from the network. We think it comes from the disk. So we have to change this. And what we ended up doing is we wrote something that could suspend the flow. So we'll like stop all the flows that's observing that key. Then update the value. Mark the next one as coming from the network, like a flag. And then restart those flows, because when we restart them, we know we're going to get a new value. And that's the value we have written. And now we can comfortably change it. So Mike showed a very simple API. This is what store allowed us. Like, this gets fairly complicated. It was very easy for us to write this thing. And the public API doesn't even know about this. And now we send it downstream. Errors are a little bit different because your data source doesn't usually care about the errors. We just send them down as they are. So there's a lot of custom code, but the simple API.
So that was great. I was really excited once we got that working because there was a feature that I've always wanted to be in store, and we were unable to do it before. Got a little help from this guy. Big thanks. But we also had features in store that worked really well and worked really well in RxJava. And one of them was that stores are actually concurrent. And there's a big difference between something being synchronous and concurrent. By concurrent, I mean any number of requests should not slow down how one response will come from the server and propagate it to them. We don't want to do them one after the other. So let's look at our store.get example again. And we're collecting it in the UI. So one fragment makes a store request for a path and saying we want cache data. We generate a flow. But then we get a second request for the same key. We get a third request for the same key. And now we have 3 active flows that all want the same data. Because the data doesn't exist in memory or in our source of truth, we'll create a loading store response and then multicast it through all 3 flows. Similar, we'll only make one request to our backend, get one response, save it to our source of truth, save it to our memory, and then multicast it to any flows that wanted that data. And I absolutely love this because I write a lot of bad code, and this makes my bad code not so bad because it'll still get throttled within the store. And this actually took us on a really far adventure of how sharing works in Flow.
So when we converted Flow to use store to use coroutines, that was a pretty straightforward conversion because it was all single. And every time we've shared something in the RxJava version, we'll just put a share, and it works. So we convert this to Kotlin. We have the flow. We put a share. It doesn't work. Because there's no share. It just doesn't exist. Which is fine. It's a new library. Like, we know what we are getting into. Like, fine. Mike said he'll write it. I mean, he knows RxJava. And after like 2 weeks, he's like, nope, let's go back to RxJava. It just doesn't work. He's like, we can't write it. I'm like, don't worry, I will do it. I couldn't.
He's a pro, is why I was very happy, yeah.
So we decided that maybe we should learn how flow works. Anyways, the thing we were missing was this property of flow, very nicely documented. It's called context preservation. That's a new concept we didn't initially understand. Let's look at an example where it might make sense. So imagine we wrote this magical share operator on a flow. And now we have one collection using as like scope, another collection using another scope. Each of them has their own context. So now, where do we collect this upstream scope? If we pick one of the scopes, what if it gets canceled? Do we cancel the other one as well because they happen to be sharing? Like, there is no way you can move a job from one coroutine context into another. There's no transfer operator or anything like that. So this is like fundamentally hard for us. And now we came to the conclusion that if you want to share something, you got to tell us where to share. So you need a scope to say that. So we need the actual upstream scope that will do the consumption of the upstream flow, and the other flows will be just getting that value in their own context. So then we start writing this multicasting class. And this is all private API. You don't see any of it, but we found it fairly interesting to implement. So I want to go deep on that a little bit. So we have these three classes. The multicaster is just the entry point. It gets your upstream flow, gives you a downstream flow in return. This channel manager is a store actor. Like I really like store actors. They're so beautiful, handles your concurrency in a very sweet way. So there's an actor that does all this complicated logic, and then producer is the one that wraps the upstream flow to talk to this channel manager. So let's see what happens when you run it. When you get a downstream flow from the multicaster, it's just a flow, nothing happens. But then when that flow starts collecting, it starts talking to this channel manager. So let's look at that relationship. This downstream flow creates an unlimited channel for itself. Keep in mind, when you want to start thinking about going between contexts, you need to have a channel. Flow doesn't do that. Flow is always in the same context by itself. So this downstream flow will create a channel for itself and send it to the channel manager. Even though this is an arrow, this is not a function call. It's just a message to the inbox of that actor. And this makes concurrency very easy. When we receive this message, channel manager says, OK, I have a downstream channel. There is no producers. Let me start collecting on the given scope. So we had a scope. When this producer eventually gets a value from the shared flow, so one is the value, and it adds an ACK into that value. So this ACK is so that it's a simple completable deferred. I don't know what's a Java for completable deferred.
The Boolean?
Countdown leg? Whatever. So it's like a lock. So it attaches it to this and then sends it to the channel manager and waits for that acknowledgement. This is so that we can control the back pressure. We don't need to consume the upstream if none of the downstream actually delivered the message. Something you need to be careful when you start using channels because they are hot. So the channel manager will send it to all of the downstream flows. And then eventually one of them will, when they get it, they emit it to their own downstream. They will acknowledge this message, which will unblock the producer. So it can get a new value. So we get another downstream flow. Now, if it does the same thing, it creates a channel for itself, sends a message to add it to the list. And if caching was enabled, we will give it the previous value. In this case, the caching is not. So stay there. A producer gives us a new value. The same thing, it gets an ACK. Channel manager sends this to both of the channels that it has. It's the same ACK. So if any of them happens to consume this new value, because they might be suspended, but if they can consume, the first one will unlock the producer to get more values. We can get a third one at this stage. It also adds the stuff to the list. But after it came, the producer decides that it doesn't have any more values. Now that's finished. We want to finish the downstream. We finished the first two. We just canceled those channels. But this third one was just an unlucky one. It happened to arrive right before the upstream flow finished. So you don't want to just close it without any values because we know there were values. And also think about it, this is for store. This is mostly for a network call. So you know, like, you would make it again. So what we do is exactly that. We get a new producer just for that one. We start running that producer. It produces values. The same thing continues. Now, if we happen to get a fourth downstream flow at this point, but then after some time, the upstream flow just crashes. It throws an error for whatever reason. That message arrives to the channel manager, knowing that the upstream flow died. This time, we just cancel both of the downstream channels with that error. Even though the fourth flow never received a value, an error is as good as a value from our perspective, so we just cancel it with that given error.
Great explanation. So we mentioned that we had store was a library that already existed. We started converting it. We added new features to it. We weren't sure if new features were buggy or not. And we also weren't sure if we understand what flow does and whether it's doing what we knew observables and singles do in RxJava. So we needed to migrate our tests as well. First thing, we just converted the test to Kotlin so that we can start using new language features. And next, we kind of looked at our test structure. We had a couple of hundred tests, and they mostly fell out of bug reports that users had over the years of this race condition or that race condition and how to store deal with it. So we took this configure store function and instead made common builders that can build both a store 3 and a store 4, our new implementation. We then did bindings back to store 3 APIs, because that's what tests were running under, and then leveraged JUnit's parameterized testing, which allows you to pass in a parameter. Our parameter was which one of these builders do you want to use, and it actually ran through our test suite using old store code and new store code. And this was great for us, both for adding integrity and for realizing that things like share, our first attempt, our second attempt, our third attempt, all just did not do what we expect. It seemed like it worked. Like he said, it worked when we put it in an app, but it didn't work when we ran our test suite. So we were really happy that we were able to leverage a project that already exists and leverage all the tests and all that knowledge that we had from community to make sure that we're starting over with a clean rewrite, but we're not starting over with what features and what validations we have in this project. And this led us to a nice piece of kit called test coroutine scope.
So I want to add some testing slides because there was another testing code you didn't go. This is a backup. So the very first time we did this migration to coroutines and in the test we just did run blocking everywhere, and we made all of them pass. And then test coroutine scope came around. Test coroutine scope is just a coroutine scope for testing. And we tried to move to test coroutine scope, and a lot of tests didn't pass anymore. Which, they were passing, they're not passing. Some of them are our bugs, some of them are their bugs. But it has two really interesting properties we want to share. First of all, test coroutine scope is very good at catching unnecessary work, like work leaks, the work you're doing unnecessarily. And the second thing is it allows you to create very interesting testing scenarios. So let's go through how this happens. I have a flow here. It's a channel flow, and inside I'm launching on a scope, sending a value, waiting for a second, and sending another value. There's nothing interesting here. If I observe this in my application, within a second, I'm going to get 2 values. So let's write a test. We create this test coroutine scope. In the test, you use this test scope.run blocking. We just want to assert that if we collect 2 values from that flow, they're going to be 1 and 2. It's fairly simple. You hit run, and this test fails. If you run it on your phone, it works. You run here, it fails. And it's also a rather cryptic error. It says the job hasn't completed yet. What does that even mean? What it tries to tell you is that it executed everything it should execute, and there's some coroutine that's still running somewhere. It should have been finished. It didn't come back. There's some inconsistency, and it doesn't know why. If we go back to the example, what was happening in this one, and we had a lot of these. It was a red herring to find why they're happening, but it's always our bugs. In this sample, I was just launching on another scope. Even though this code works, There's a problem here, because if you stop collecting from that flow, this myscope.launch, that section will not be canceled. It has no idea that the other one is canceled. It will only ever cancel when it tries to send a value to that channel, which is canceled, and it will realize, oh, OK, let me cancel. So we had a bunch of leak work here and there in store. It will just keep running for no reason. But when we were testing with run blocking, we didn't catch any of these, because it could just keep running. But when we tried to move to test quality scope, suddenly all of these problems showed up. So easy fix here. We just get rid of that scope launch. And now we run the test. It will pass. I will also pass in a duration like 100 milliseconds or so. So we have a test that has a 1 second delay in it, and the test passes less than 100 milliseconds. It doesn't make much sense. So what's happening here is that the time is fake. There is no real time in test coroutine scope. It's a controlled time. And the fact that it's a controlled time is actually allows us to create very interesting scenarios. That's the second part of why we like this. So imagine you have some test subject that receives like 2 flows. And you send it to them, and you want to create different scenarios of different values coming from these flows. So we'll just say 1 flow, another flow, and then give them to the subject as a merge. This test, this code is predictable. I know the values from the first one will go first, and the values from the second one will go next. If I want to change the order, I can just say delay 1 on each. I'll make the second ones come first, and the first one comes later. And I can even go into more detail to say, OK, I want 2 values from the first one, and then 1 value from the other one, and then more values from the other one. Just keep in mind that this delay is fake. It doesn't really delay for that. It just reorders the execution. And imagine writing a library like store. You have a fetcher, you have a disk. They're all coming in, like they're running in parallel. They're independent of each other. They might send values in different orders. They may crash in different orders. So we wanted to create test cases for all of these. And heavily using delays, we were able to cover a lot of different test cases and make sure store handles it. So I know what I did. I just recommended using delay or sleep for your tests.
We expect to see that on Android subreddit within the next 5 minutes.
Yeah. I'm behind it. Because like, this is, first of all, this is not real time. It doesn't slow down your tests. It is predictable. And this is very useful to create very edgy race conditions that you cannot easily create otherwise. So I don't know. I really enjoyed doing this. And it might be useful if you're writing a library that's also highly parallel, like store. What's next?
So this started as a library, kind of like a pipe dream that I had to try to learn a little RxJava. When I worked at New York Times, I was delighted that I was able to convince them to share it with the world. Since that time, we've gotten over 30 contributors externally, and I actually moved on from New York Times 2 years ago. They've been great partners continuing in this project and making sure it's up to date and making sure that it's still working as well as I always wanted it to. But today, we want to announce Store 4. And what we want to announce is that Store 4 is going to be moving to Dropbox. We're going to do active development on the Kotlin version of Store within the Dropbox repo. And we want to open this up as a call for action. It's already a community project. This is already something that we're getting community contributions from.
The community.
The community, yeah. And you know, we're releasing this as 4.0 alpha right now. We really want to get feedback from everyone of, does this API fit your use cases? This was a tiny library that I wrote just to use at New York Times for the particular case that we had. But it's gotten to something much larger than that. And what I hope that this will become is the definitive implementation of a repository pattern on Android, and we can't do that without all of your help. So once again, I'm Mike Nakhimovich.
I'm Yiğit Boyar, and don't forget to vote. Thank you.
Thank you.
Yes, we are good. Hello, everyone. Yeah, sleepy? Last talk of the day, is it, right? Okay, it's fine. So then we're going to do something complex. So, you can actually go to sleep with some substance. No, I'm kidding. How many of you have tried Kotlin Native? All of you? Well, then, bye. No, I'm kidding. So, hi, I'm Eugenio. I'm a developer advocate for Kotlin multi-platform and mobile at JetBrains. I generally don't introduce myself, that's why I forget. And this is sort of the story of my journey in trying to discover Kotlin Native. Normally, I talk about this in a multi-platform setting, in the sense that I talk about Kotlin Native as in, you share code across platforms. But Kotlin allows you to pretty much have the granularity that you like, in the sense that you can share stuff, but you can also go full in even a single platform. And sometimes even like the thought of where does Kotlin end and where does the platform start can be tricky. And so what I wanted to do was try to experiment and push as much as possible the limits, let's say, of what is possible to do in Kotlin Native only in Kotlin. Now, specifically, when I say this, I mean macOS and iOS. Because at the time, what I wanted to do was create an app, and all the samples online are for iOS, not for macOS, for example. There's one little sample, but it's not great. And also, when you open it, I'll show you, more or less, oh, actually, this is already the beautified version, but more or less, this is what you get. It's not extremely pretty, but yeah. Also, the output of that is a KX file, which is like a binary file you can execute. And that's not an app. Like on macOS, apps are these things with an icon. You launch them, they do stuff. And there was nothing like this. So I was like, what am I missing? What is the secret here? On top of that, Xcode. Have you ever used Xcode? So sorry. So sorry. Yeah, so I wanted to see if I could try and avoid that. And just to make things more complicated, AKA fun, I thought, well, you know what? Do you have a Nintendo Switch? Yeah, a few? OK, perfect. Yes, yes. And you all know also that presentation remote that you can sort of point in the air and the cursor moves, right? Yeah. So I said, well, I have a Nintendo Switch. I don't have that. And I have really bad ideas. So why not try to make it with the Nintendo Switch controllers? In Kotlin Native, of course. And now I'm going to show you the project that came out of it. It's going to be very flexible. So if at any point you want to ask me anything or you want more clarification or whatever, just stop me and we can figure it out. So where to start? First of all, there is a website that I hope now I have internet. Let's see. Oh, yes, OK. So it all starts not in Kotlin, but on this amazing website. This, can you see? Is it big enough? Well, this website is amazing, and they pretty much reverse engineered a lot of things about Nintendo Switch. Well, I mean, of course, like hardware and stuff, protocols, etc. The really interesting part, the one that we are interested in, is mostly Bluetooth stuff. So if you go in here, and it looks scary, but once you get it, it's not that much. You have all these commands that you can issue, get back stuff, etc. Of course, all the samples are like C or whatever. And you work with bits and bytes quite a lot. Now, you don't have to know how this works, but more or less, you have this HID manager, which like can enumerate all the connected devices. By the way, fun fact, Bluetooth and USB have pretty much the same protocol. So you can essentially make one and the other work the same way, which is really cool. And so you do this, and what happens is that you enumerate the devices, you open a specific device, and then you can start sending reports, they're called. Well, they're like requests for more data, for something, and then you get things back. And you communicate like this, blah, 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 blah. OK. So started here, and I wanted to do it on Kotlin Native. Now, the API for like Mac OS for this stuff are not even in the Foundation framework. I don't know if you know the difference. So there's Foundation, they call it, which is this higher level framework where you have all the basic runtime stuff. But then that's built on top of Core Foundation, which is the even lower level one that essentially it's like really low level, to the point where even the reference counting is different in certain ways. Now, Kotlin interopts with the Objective-C runtime, the ARC, nicely for the foundation stuff, not for the core foundation. So that was something that I had to figure out. I'll show you how it works more or less. So they are a lot more lucky than we are in the sense that on iOS you can change between the types. It's called toll-free bridge, if I'm not mistaken. And I'll show you how it works. Yeah, so essentially you can convert between one and the other normally without doing anything special. But if you are not lucky, so let's create a new scratch in Kotlin. Can I put it here? Yes. Does it work? Can you see? OK. So normally Kotlin types are not a problem. You can say something like, I wonder if I'm not having the module stuff set up here. Wait a sec. Come here, 1 second. Let me just, module, that's why. Right, if I do this. Yeah. Yeah, no? OK. No, it doesn't pick up the, just create a normal file, because otherwise it won't work. Where are we? OK, new. OK, now, as we were saying, yes. You can do things like, you have a val, foo, whatever. This is a normal Kotlin string. Why does he complain even? Oh, right. I should probably mirror the screen, but it's still a mess. So, normal Kotlin string, everything's fine, sure. If you want to make it an NS string, which is from the Foundation framework, you can just cast it. So you say as NS string. And yeah, it does complain, but it is actually fine. For this very reason, I did a few extensions like this, if that's, or is it as? Maybe. Yeah, I guess it is. Yeah. And then this way I remove the cast, whatever. And this is fine. Every time you convert, it internally changes like the reference count so that you sort of borrow the object, and when the collection happens in Kotlin, the other side is not concerned, so that's fine. But if you want a CF string, as in core foundation string, then that's different. And if you look at all the core foundation methods, they're very C-like in the sense that instead of taking an object, because there's no objects, you need to create it. And to create it, you need to do something like, well, let's have a function just for the sake of, right. So you do something like cf create, if I'm not mistaken, or cf string, I guess. Yeah, and then you have all these things that essentially take bytes, and you need to allocate stuff in order to just do something simple, like creating a string, which is intense. And not just that. Once you finally do have one of these objects, well, if you create it, you own it. So you need to remember to release it. And if you get it as part of a method or something, you need to retain it. So let's say show interest that augments the count, and then you need to release it after. So you need to do something like cf retain, and then you pass the whatever variable, and cf release on the other side. And the point is that this is sort of scope-based. So as soon as you get it from whatever, you need to immediately say, yes, I want to retain this. And then at that point, it's your responsibility to unlock it, let's say. And you can do this multiple times as long as the count of how many times you retain and release is even. So that's fine. OK. To make it simple, I created a few extensions that I can show you. So let's see. I'll actually start by let's try to actually do this now. Display. I will start mirroring, because why not? Arrangement and mirror. Boom. OK, it's not too bad. I wanted to see if, not brightness, whatever, but can we scale it a bit like, OK, yeah, sure, that works. All right, oof, it's a bit, can you see? Oh, I love it. It's ginormous, I love it. OK, let's even do this. All right, yeah, so, all the boilerplatey conversion from one to the other, blah, 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 blah. This, I'll probably open source this. You could get this technically as supported by Kotlin. They haven't listened to me yet, so it's not there yet, but it might come. The problem is that if you need to do any low-level thing, you'll need to do this, and it's whatever. And so, OK, fine, that's as far as this part goes, sure. And why am I saying this? Because if you want to, again, talk to the Bluetooth stack, essentially, you need to use APIs from Core Foundation. So you need to deal with this, unfortunately, and that's error. All right. The other thing, so more or less, the whole lesson was, it's not even that you don't understand or don't know Kotlin Native, is that you just don't know the platform. So in the end, what I had to do, despite, the wish is always, oh, by using Kotlin Native, you're just going to have this silver bullet. You don't have to learn anything about iOS, about macOS, whatever. That's not the case. If anything, you probably should learn about it even more to be able to do things properly. So that's what I had to do. It was actually pretty interesting. And again, so you start to understand things like, what is an app? It's a folder with one difference. It has a specific sort of manifest file. It's called info.plist. So I'll show you, for example. So yeah, you see it here. It's like an XML thing. There's not much, just a few things. All of this, of course, is documented. You can find it on the Apple documentation and stuff like that. Or you can also do a trick. You can steal it from other apps and modify it, whatever. Yeah, so that's it. And in order to make this work, the only important part is that it's side-by-side where the execution binary is. So in this case, if you look at the build folder, yeah, put it here. And just because this is there, then it works. Then it's a real app, and it just runs. So that's the first part. The second part is, if you create an Xcode project, you just have this main entry point where all the application is set up for you, and you just write your app delegate, blah, 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 other things. But I don't want to use it here. So how do I set up an app? What does that magic do behind the scenes? That's what I wanted to understand. So every Objective-C app is a C app in the end. So it all starts with the main method, right? And you normally have an annotation, if I'm not mistaken, called NS application main. In this case, we are sort of doing it by hand. So how? We do create an app delegate, which is just a class that extends this protocol. I don't even, if you want to see the, yeah, you probably don't, but there's a lot of methods. It's the equivalent of an activity, but delegated, so it just calls the methods for you. You need to extend NS object because you're in that realm. Still extends any in any case, but still. And then, so if you really, because this is low level essentially, right? So you need to decide where you want to paint, and so you need this display rect to say actually, on which surface your thing is going to draw. And then just to make it clean, I passed a callback that from the outside, you give me a way to stop the application, and then from inside the UI, I can actually call that and stop the application, for example. Okay. Yeah, this is just, just to make it easier. And then mostly what you need to do is to create a window if you want to draw. And so you can just essentially read what's here, but, oh, this is interesting. So this is a struct, which means it's not really an object you pass by reference. You pass it by value. And what that means is that it literally is copied, everywhere, except Kotlin doesn't have support for that, really. So this super neat trick that they use is that you have this use content function, and what they do is that they copy it in memory temporarily and actually do create an object. And then from inside of that, you can access it, and as soon as you're out, it's deallocated. So it's a nice way to do it. If you need to create it, I'll show you later, but you literally allocate it, you do something similar to initialize it, and then you can just launch it wherever you need. And this is the real trick. The real trick is just here knowing the platform and passing the right styles. It's as easy as that. It's like saying on Android when you pass the wrong style and you get the gingerbread theme. It's exactly the same. And once you, by the way, there's a lot of flags that are really interesting. You can make things without a shadow, with a weird shape. You can make them so that you can't, resize them, or you can't do whatever. It's a big framework, of course. Once you have that, blah, 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 you create a window. This is still part of the sample original. You can give it colors, etc. Blah, blah, blah. OK. And then you actually compose the UI, which is the interesting part, right? So here, again, if you wanted to use Xcode, you would have storyboards and all of that. And you can, of course, load storyboards programmatically if you want to. I just didn't really want to use storyboards at all. And you can do everything. Actually, behind the scenes, even storyboards, they're just programmatically loaded. It's like the XML for Android, if you know that. But that means you can also programmatically create any element of the UI. And this is what I'm doing here. And so you can even make it look super Kotlin-y and just keep saying button, blah, blah, blah. So for example, this is a function I create to already pre-pass some parameters. And then I use it here. And it's super clean, right? The way it works. Interesting thing. So you start seeing all these little bits of platform-specific things. For example, if you want to give it a callback, right? So in this function I created, it takes a lambda. And you think, sure, no problem. I'll just set the callback, right? But you don't just set the callback in Kotlin Native, or I guess on the foundation framework. You have to put this sort of annotation so that then the runtime knows that the dispatch is on that method, and it's sort of magically sent there. It's kind of weird. So I abstracted it, because why not? I created this callback class, and this is what I was talking about. This is a Objective-C action, which is a special thing that happens. And just with this, it would work. With one little caveat, as soon as you're, like technically nothing is really keeping a reference to this. So as soon as you are done setting it, and then you do something else, you come back, you try to invoke it, it might be deallocated by then, which is a problem. So what you do is you need to associate it with the life cycle of that object. And this is literally talking to the Objective-C runtime, okay? We are just saying, when you do your reference counting, whenever you're essentially deallocating this, then also deallocate that. Otherwise, don't. And yeah, so because it's a weak reference also. And with this, it just works. And it works, it's not a hack, it's actually how the platform works. So, it's nice. Little thing that I really love, normally when you do this selector, because that's the non-type safe part that I don't like, this action, they want you to pass here the name sort of like this, right? What could possibly go wrong? Like, I don't know, maybe you just do something weird, and then it doesn't work. And so we can use the amazing power of Kotlin and just use like a property reference and then just take the name. It's always going to be updated. Fuck it. OK. So this is one trick, for example. Yes. Out of the many things you can come up with. And you can really start making it look Kotlin, essentially. So blah, blah, blah. We create the window. On the window, which is like a root view. We added the subviews, etc., blah, blah, blah. That's it. And this is the main entry point, right? You have these like delegates, essentially, functions that whenever things in the lifecycle happen, then you get called and you do things. So here, again, like this was just hacking around. Like a few things I did in detail because I wanted to show stuff, but this is super hacky. Here, for example, we call this main method, which is where I put all the logic about the Joy-Con stuff. So I'll show you. First of all, have you seen the concurrency talk from Kevin? If not, I'll wait. You can watch it. No? OK. But essentially, I also wanted to demonstrate how it would look like if you wanted to do like sort of a Redux-style pattern where you have immutable state, you sort of emit events, and then you reduce those events and have one place where everything is computer as far as state goes. But then everything else is in different threads and does whatever it wants, and it should still work. And let's see if it does. So actually, let's start from this very method before anything else. If you want to start a thread, so normally, when you talk about asynchronous stuff, you say something like, I want to do an operation. I want it to be in the background, and then I want something back. That's it. In this case, it's very different. You want something that runs continuously, like a loop in a loop, let's say. So you really need like a thread, or at least a place where that lives. And in this case, I did exactly that. I did like a thing so that it could live somewhere. And the way you do it is that you create an NS thread, and you pass it a lambda. And the trick is freezing the lambda. Otherwise, it will not work. And you know how it is in Kotlin Native. If you want to let something go in other threads, you need to freeze it. So if it's frozen, you can let it go. And then this is the interesting part. So again, if you know Android, you know like handler threads. So event queue happening, and that's how events are processed. This is the same here. So we get the current loop because every NS thread has a loop associated. This is actually the low level. Every time you see CF, it means core foundation. So you get the low-level loop, we retain it, and then this is just something I created. I was missing it from Java, so I created a closable interface because you have to. And and this way, I essentially made it so that in the init of your whatever thread code, you already have access to the cleanup method to the thing. And then you have a dispose method where whatever you created in the init can get disposed as well. And this is how it works. Well, you init it, and then you make the loop run. And so this is blocking, essentially. This will wait until there's new messages on the thread. When there are messages, it will just continuously update them. The only way to stop it is to stop the loop, or I guess kill the process. But and you stop the loop from here. So, I already provided both the initializing and closing behind the scenes. You don't even see it, essentially. And then we dispose it at the end, blah, blah, blah. We already set a name and start it. That's it. So you can imagine that from here, anything inside will be on a different thread. So let's go back to that. Did I go too far? I did. OK. So we start this reducer thread. Cool. Then the point is we sort of want to have a circular dependency, because we want data to flow in one direction only. OK? So we want whatever is happening, like side effects, to emit events. We want the reducer to see the events, reduce them in a new state, and then send back a new state. And that's the cycle. Okay? So in order to do that, since we want everything to be immutable, we have to do a trick, and it is using this atomic reference, which is sort of a placeholder where we promise there will be something on the other side in the time that you're done. For now, there's nothing, but that doesn't matter. And we also keep one just to have a place for the state to live, like the latest state, so that we can get it back and set it. Once we have that, so again, there's this, in order to use the platform, I started just digging in documentation, like how do you send something on a loop in a different thread? And there's a bunch of things. The easiest way, I guess, is to create a port, which is nothing more than, the way it works is that you can stop a loop by either having a timer, which is time-based, interrupt, or a source, which is a source of events that can stop the loop, make it process stuff. Otherwise, the loop would just wait forever. If you don't have any sources, actually, it closes down. So you create a port, and this is, again, like a helper, essentially, where you see, again, all the retain stuff. It's a bit annoying, but it's not too bad. Also, the runtime tells you if you forget, because by the time you close the process, it will tell you that there were leaks happening because you didn't properly release stuff, for example. And so, for example, this is one of those things, or is it? No, this is not, whatever. We create this port. You don't need to know all the details, but we need to often do this thing with passing callbacks. I don't know if you've seen this before, but if you need to go through a C function, you can pass a live callback, as in a lambda that is actually stateful, that has references to the outside. You can't. It has to be completely pure, completely static. And since they know that this is the case, they always make it so that like the first parameter, or a parameter, is the mutable part that you need to actually execute the lambda. And so in this case, the mutable part is, well, more than one, I guess. And you do this sort of wrapping, unwrapping. So normally, a Kotlin object lives in your scope. But then as soon as you sort of leave the scope, it's gone. In this case, we are crossing boundaries, going to C, etc. The runtime would have no idea when to release and keep stuff. So we tell it explicitly, please create a stable reference to this. Once you have that, then of course it's your responsibility to release it as usual, but you can pass it as a C pointer. And then suddenly, you get it, see the info parameter, you get it back on the other side, And then on the other side, you can put it back as a stable reference, get it, and then use it. And this is how you do the whole thing. It looks weird, but it's actually really clean in the sense that you can do the same on the JVM or anywhere else where your logic is completely stateless, completely blocked. And then you just have this, you inject these arguments on top of it. Blah, blah, blah. Again, you don't need to know all the details, but the nice part is that by having this closable abstraction, you can just put all the cleanup in one place. And then you have these objects that you already know that are going to be clean in the end. You can even chain them, and they just get closed all together, so that's fine. Blah, 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 blah. So sorry, let's go. Yes. So I promised you to show you a struct of how that would work, and this is it. So this is a struct. Actually, if you look at the type, it will probably look, well, it even tells you it's a struct, okay? And if you try to create it or something like that, it would complain very much. Yeah, it would just want a row pointer to it, which it's like the opposite. You want the pointer in the end, but you don't have it yet. So you do this alloc, and in order to allocate any memory, and this is the point. So as long as you do Kotlin, pure Kotlin, without calling any C or platform-specific functions, you don't need to care about memory, which is great. If you've seen around, we have not really touched memory except for, again, platform-specific things. There are times, though, where you do need to interop, and you need to provide a scope, generally, where the memory will live, right? What is the life cycle of this thing? How long do you need it for? And in this case, we need that for creating the struct, and it is this memscoped part. With this, then you can finally, do the thing. There's other ways, but this is the, let's say, safest. And one thing that it took me a bit to understand was, sure, but I'm passing data to something else. What if, I don't know, they live longer than this scope? What happens then? And that's generally not a problem, because, again, since the C world works like this, they all know that the moment they get something, that's something, and it's a pointer, it could go away. So they just, keep it for themselves. They keep a copy, a reference, whatever. And so by the time this function returns, you can be sure that the memory is not going to be needed anymore. Either they used it, and that's it, or they kept a copy, they kept whatever. So it's fine. And if you start thinking like this, it makes it a lot simpler. And then I started realizing that the documentation also tells you, in the specific cases where that's not true, you will know very well, and so it's fine. Blah, 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 blah. And see, yeah, we are creating this source, which is, they're very verbose, these methods, extremely. And you add them, et cetera, et cetera. Okay. So once we have this port, sorry, I forgot the important part. The interface for the port is super simple. You just send stuff to it. That's it. And I have abstracted all the serialization, deserialization stuff. So you can just send anything, and that's it. And we even pre-freeze it, because then we are super sure that it can be shared. And let's go back again. Yes, so now we're coming back to the main thing, right? We create a port for the events. So this is going to be used by the side effects parts to tell the reducer that something happened. We essentially say exactly, yeah, and when we create the port, that's also the trick, you already have to provide the callback. So it's like, when this port will receive a message, what will it do with it? And so in this case, we receive an event, we want to, reduce the state. And so we say, oh, actually, that's not needed anymore, I think. Yeah, no, it was written. Damn it, never mind. Yeah, so we said, okay, this is the event. We reduce it. This was the old value, which we dereference from the atomic stuff. And atomics have the peculiarity that you can freeze them, although they're still technically mutable, which is sort of a fringe thing. But so this is the only reason why this is fine, because at some point you do need a bit of mutability, but it is a very controlled scenario. And as long as you don't introduce cyclic dependencies, everything is fine. So you're going to be fine. All right. And what happens is that, again, like we just reduce, create a new state, set the state in the reference so that we have it for later. And this is the promise we had before. If there is something set up here to dispatch back, then we send the new state to whoever is listening. And once we have that, that's it. We use an also because this returns a closable, so we want that to be the last thing. And that's it. And then once we are there, just because, we start another thread, because we want to compute the state on one thread, but then we want to handle all the device-specific stuff on a different thread. And, I mean, just because I abstracted it, high level, how you want this to work is, because we are working with immutable, actually, I'll show you the state first. I think that works best. So the state is super simple. You just have an ID for devices that we generate. It's like a monotonically increasing integer, right? So we just want to know what was the last device that was ever found and what devices we decided to keep because they are actually useful for whatever. That's it. The type of events that you can do are a device was found, and this is the ID, and this is the name. A device was removed with this ID, or the fun one, a number of buttons, state has changed. And so you're going to get this, thing that you'll see later, and you can know exactly what was pressed, etc. Okay. These are all the events possible, and this is all the state possible. So of course, we want to then know how to handle that, and I'll start by showing you that, which I think is the easiest. Where are you? Board, blah, blah, blah. Ah, yeah, this is the reducer. Super easy. So you're doing your reducing, blah, 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 and then you say, when the event is a device found, then you say, well, if the name is one of these two, because that's how it works, like all the Joy-Cons have this name via Bluetooth, so you can't go wrong, essentially, then fine. Then we return a new device, otherwise whatever. And then we create a copy of the old state, and we say this is the latest ID, blah, 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 and we add the device to the set. That's it. If the device was removed, of course, we want to say, OK, so we essentially remove it if it was there, etc., trying to avoid creating an extra copy, etc., blah, blah. And for the buttons, I didn't do anything now. We can do a print here, but ideally from here, then you can, I don't know, bind it to an actual button click or start moving the mouse or whatever you want. Update the UI, for example. So this is all the real business logic, I guess, of the app. Once you have this, then you have this sort of driver on the side to drive the side effects related to the devices. And that's what was up here. So, OK, devices manager. And you'll see one other thing here, this thread local. So this is the place dedicated to actually, making all the side effects possible. So this is the thing that's keeping track of all the dirty stuff, while your pure logic lives up there, in the cloud. This does all the work. And so what happens is we made it, abstract just to make it a tiny bit more clean. But apart from that, it's quite easy. So you want to know what happens when there's a new state. You want to know how to open a device, how to retain and release a device, essentially. And then, again, you keep a var for yourself. You keep a list of devices and open devices. And again, because of the fact that this is thread local, you can have these vars, and it won't blow up. Blah, blah, blah. Inside of this, we create another port, which is the opposite port, the one that actually receives the state. And we can do already the closing up, etc. And it starts to become very clean once you have this symmetrical pattern up and down. Like, for example, in the open devices, it's literally just device ID related to a closable. So you don't even care what or how, because this is not going to handle the devices as the business logic. This literally keeps a reference to them so that the business logic can use them if it wants to. Otherwise, they're gone, and we don't care. And yeah, so just pretty much boilerplate, essentially. So we increment the device ID whenever there's a new device, blah, 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 blah. We can add it, etc., remove it, blah, blah, blah. So this is really not very interesting. It is more interesting when we use it. Are you here? So we subclass it by providing the actual methods like retain, release, blah, blah, blah. Open device, I'll show you later what this does. This is the actual Bluetooth stack then working. And then pretty much the last part is what happens when you have a new state. And when you have a new state, two things can happen, essentially. You either, the business logic decided that you should discard some devices, or that other devices should be opened. And this is what we're tracking here. So we say, well, OK, anything that is not in the state should go. Everything else should be kept. And then we iterate, remove stuff, release anything that we don't need anymore, essentially. And blah, 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 etc. And then we start checking the open devices. And all of those that are not to be kept, then we release them as well. And then for all the devices that actually have not been opened yet, we do the opening. So we open it as a, like methods, and I'll show you later the implementation, the like Bluetooth stuff. But then the really interesting part is that we set a callback to say, whenever this device is sending data back, I want to do something with it. And this is where the bit craziness starts. To be fair, I did this just because then it would easily fit in one screen. There's ways to abstract this so that it's not that painful, of course. But yeah, like you can make it so that you can use the serialization if you want, not out of the box, but there's ways to do it. I even wrote a small preprocessor that you define some sort of models as data classes, and then it generates all this for you, but whatever. Again, there's many ways to abstract this. But the point is that if you actually look, Bluetooth hid information. So going back to the documentation, there is, where are you? Here. So when you receive this input format, this is the ID of the input format, you have this bytes payload happening. In particular, we are interested in the button status, which are 2 bytes, 1 and 2. And then inside of that, for each byte, every bit corresponds to a button, right? And that's what we're trying to get. And so we take the 2 bytes, and then one by one, we do these super ugly bit shift operations just to get out if the thing is actually clicked or not. Once we have it, we send, and that's it. Okay? And this is, again, like, this is the low-level work that the business logic doesn't really want to do. This is literally serialization, deserialization, not deciding anything, really. Yes. And that's it. Finally, once we have all of this, so we created this other thread with the devices manager, etc. At the end of all of this, what we do is we actually set those references at the beginning, the sort of promise that said, please give me a reference so I can send you back the state. We do set it here. And then this is, like, up until now, nothing has happened yet. This is all set up. And that's the beauty of actually making things immutable. You declare an initialization thing, and then everything else just flows after that. And so what happens is, this is the real now start of what you're doing. You start searching for devices. You search for devices, and once you find one, you get the name, you send it as a, where are you? As a method here. And you already set a callback that when the device will be removed, if ever, you remove it and you send it as an event. That's it. that's the end of our setup. Notice the plus because I'm chaining the closables, because why not? And then it works. The only thing you have not seen, and I can show you if you want, but it's pretty boring. This is the low-level, I don't know, search for devices, where you literally create this, call this IO head, blah, blah, blah. You pass all the things, you do all the boilerplate, etc., which again can be abstracted, but here you see. And then you have this symmetrical disposing, thing. And you only have to do this for the core foundation, right? There's not really any point in doing this sort of cleanup unless you're managing memory directly, which hopefully doesn't happen often. So, and once we have all of this, it's done. And now I want to try to show you if it works. This was the preprocessor running. This I was playing with language features, because why not? And let's see, what could possibly go wrong? So, linking. And while it's doing that, now I, of course, made changes until the very last minute, so there's a very good chance that this will not work. But behold. So the trick is that you press the sync button, wait until the LEDs start going around. We can see, by the way, in the command line that this is running, and it's now open and listening for devices. Then you go to the Bluetooth preferences. Can I go on the other side? I want to go on the other side. No. It doesn't let me. Okay, let's do it differently. Again. Okay, not connected. We try to connect. Go back on the other side. Oh, yes, connect. Wait, generally when it does that, oh, whoa, that's not expected. Null pointer exception, wow, that's something. Kotlin is null safe, remember. Where? Because the thing, no, actually, okay, I know why this is, yeah, it's my fault, don't worry. Let's start it again. I think every time I reconnect it that way, it does a weird, ooh, 1+, no. It does a weird, like, how can I explain this? Sort of like a mid-state where one part of it was there, but the other was not. And so it's not the way you expected things to be in that instance, because you need to try again, essentially. Oh, but, okay, there you go. So it actually did all the things. Yeah, okay, so we're here. Stuff happened, and of course. And then you can crash it remotely by pressing a button. Amazing, amazing, ladies and gentlemen. Again? No. Okay, so obviously I broke it just because. Why is that null? Oh, because I'm not passing any context. I totally broke it. How much time do we have left? Is it like none? Do you want to do it live? Because, no? If you want, like, yeah? Yes or nay, yeah? Okay. So, what we want from this is to get back an input report, lambda, because this is a tape alias, actually. This is a tape alias for the lambda, right? So what we are not doing is actually passing the lambda back. And we totally need to do that. So yeah, we're here. So we even create the reference, even dispose it, just never pass it to that. And so let's say call back ref to a pointer. And even just that might be it, maybe. Let's see. Where did I put it? Do you have any questions in the meantime? You look at you have a question. No? It's just your face. how long did it take me to build this? You mean the first hacky version? Like, well, once I figure out the other things, like, oh, you need to initialize the app this way, or you need to do the other thing the other way, I want to say 3 or 4 hours, maybe, something like that. It's not polished, obviously, like it's very, thrown out there. But even then, oh, come on. Let's see. Still? No, wait, it can't be. Did it even compile? No, I don't believe this. Say again? Yeah, but it really shouldn't be null. Like, the whole point is that we are creating a reference to it so that we get it back. But then at this point, let's debug it, because why not? That's also one super neat thing that you can do, and it kind of just works. Did I put the line or Kotlin? Well, I hope it's a line. OK, so this is the beginning. I probably have to then press. All right. Oh, wait, did it already crash? No. But then, wait a second. I think. So where did we put the breakpoint? Here. Let's actually. Are you really? Maybe that's a problem. Might be. Actually, let's do it like this. Let's say this before, and then we can just do this. And then I'm hoping, finally, OK. Trick, you should use the line breakpoint, because that's a native one. Super confusing. It's already being fixed. Don't worry. You'll have one breakpoint, essentially, or at least a very well-named breakpoint. And so again, and by the way, you can access pretty much anything on the Joy-Cons. You can access the gyroscopes and motion sensors, essentially. You can access the infrared camera. You can access the vibration, and you can make it vibrate in ways that are crazy. It's like a subwoofer, pretty much. Time is over. Well, you'll never know if it works now. There you go. But we are working on compilation speed, so next time it's gonna work. Yes, come on, yes. Yes, that's fine. Where are your context? So it is there. Then what is your problem, context? Come on. Yeah, but I think that's supposed to be working. Well, we'll never know now. Guess it's something inside the Lambda. Next time, we'll have a full debug session just for that. Thank you very much. And remember to vote.